happening. So thanks very much everyone for coming along to our Soil CRC Communities of Practice for Western Australia online workshop. We got so close to being able to come face to face and catch up, but it's not to be. But thankfully we've got the technology so we can still connect and learn and engage. So I appreciate you all coming along, and I'm pretty sure that there'll be some others joining us at some stage along the way as well. So I just also want to say thanks to our presenters for being so agile and being able to change our presentations a little bit so that we can meet online. So welcome to Richard Harper and to Andy Gulliver. And thanks very much for making yourselves available. And thanks very much to Richard for your support in bringing this together today as well. We had a few other exciting things in store, but it's not to be, but there's always next time. So that's okay. We know what we need to do. So we'll get on with that. I'd also like to welcome Chris Wyman, who is a colleague of Andy's, and Maria Ten, who's a colleague of Richard's from Murdoch University. So welcome along, and thanks for joining us. Feel free to participate and engage as well. So we'd love that. So for today, we're just welcome. Richard is going to cover off on some soils and landscapes for Western Australia. We'll have a bit of a break, and depending on how Richard's going, we might have a little break in between Richard's talk, and then we can come back. But we'll definitely have a good half an hour break at about 10:30, and then Richard Bell will come in and run us over some organic matter and soil chemistry. And then Andy Gulliver from CWise will talk about organic amendments, some types, properties, benefits, uses, some of the practical aspects of that. Then we'll have a half an hour lunch break from about 12:30 till 1, and then Lynette Abbot from University of Western Australia will be joining us to take us through some soil biology. So yeah, that's the plan for the morning. If anyone's got any queries or questions about the program or how we want to run it, I would encourage you to please use the chat, pop in any questions, or if you would like to ask a question, then please feel free to ask a question. I know it's difficult on this online space, but we really want to try and make it as interactive and as beneficial for you guys as possible. So if you have any specific issues or specific questions, then please feel free to ask them. And if you feel like you can't sort of interrupt, then pop it in the chat, and then we can catch up on it at some stage. So, and if you've got anything of your own bits of information that you would like to add, or experiences or resources, then please feel free to pop those in the chat as well. So it's really about sharing as much as we can while we're together. So with any questions, I'll give you the opportunity to ask. No worries. Well, like I said, at any time, feel free to pop in, and no worries, Chris. Chris just letting us know his video is not working, but that's okay. No worries. Yeah, and I might just ask you to pop yourselves on mute while the presenters are happening, so that we don't get too much background noise and they can feel confident to present. So we'll start off with Richard Harper. So thanks very much, Richard, from Murdoch University. He's going to kick off the day today, decoding the soils of southwestern Australia. So thanks very much, Richard.
No, thanks, and thanks for the chance to talk to you all. What I was thinking, obviously Zoom's a little bit hard, but if you do have questions, points of clarification as we go along, sing out. Sometimes you can sort of just end up in a trance, and I'll sort of quite merrily talk for 90 minutes, but yeah, I might sort of lose some of you on the way, but yeah, the aim is to make this as useful as possible. Very briefly, just by way of introduction, I'm at Murdoch now and do teaching and research. We've got research projects predominantly at the moment with students, a few on carbon mitigation using the land, and I've got one person working on mangroves and carbon up in Vietnam, a gentleman working down at Wickerpin on carbon in a 20-year experiment we've got down there with saltbush and various species of trees, a little bit on urban forestry, water repellency. Had a couple of recent students with Richard, got a lady Mai working on soil water repellency under native bush land in probably the Murdoch campus, because we don't have a huge travel budget for that, but there's plenty of bushland and things to sort out. And then Maria, who's joined the talk as well, and she started last week, and she's going to look at soil water repellency in the wheat belt and the role of radiometrics and other sensors in predicting where that's going to occur. It's by way of background, over the years, I've spent quite a bit of time on soil surveys with CALM for 15 years, and we did a lot of work with plantation site selection, and charging around the region with backhoes and drill rigs, digging deep pits, and that might be where Richard snapped the photograph of me, and basically trying to work out how to avoid calamities, because if you plant trees in the wrong places, they either die or don't perform particularly well. But yeah, and also sort of trying to fit them into farming systems. And that was sort of right across the region. So that's probably enough for now. So what I was going to do was see if I can drive this thing. So basically, farm productivity is controlled by soils and climate, which gives us a statement of the obvious, but a lot of the soil management requirements, so things like nutrients, erosion control, salinity, acidity, and water repellency, they don't occur randomly in landscapes, but are soil related and can be related to the soil pattern. And there are patterns in the wheat belt, but over the years, a number of people have spent quite a bit of time trying to work out what's going on and explain the pattern. And predominantly, a lot of this work was done in the 1950s and 60s by people like Bill MacArthur and Maurice Mulcahy and Eric Bettiner. They literally spent years working out what was going on. So I'll attempt to explain some of what they found. But just as a preamble, the soils here are challenging compared to those elsewhere in the world. You've got river deltas, which are incredibly fertile, and soils formed on volcanic ash, very, very productive. But the soils in Western Australia are quite different, and they do present a series of challenges. And I guess that's basically what you folks are doing in your jobs, is trying to sort out some of the challenges we've got. So there's some typical wheat belt soils taken at various times and showing them in all their glory. And what I'll try and do is explain how some of those soils have developed, and also the broad pattern in the landscape. And as you'll see, that's due to the geology, but it's also due to processes that have occurred in the landscape over a long period of time. These are very, very old landscapes. I'll attempt to describe how these patterns and processes have resulted in the major soil properties. And obviously the southwest is a large region. There's many soils, but I'll try and pull out some of the major properties, and then right at the end we'll talk about how that might affect how those properties affect soil management and some of the approaches that people have devised to manage the soils. But it all starts with the broad geology of the region, and you can see. Can you see the pointer when I point on the screen? Yeah, that's good. Okay, so basically, at the highest level, you've got two broad geologies. On the right-hand side of the Darling Fault, you've got very old, predominantly igneous rocks. They're up to 2.5 billion years old, very, very old. And on the left of the Darling Fault, you've got sediments, and that's the Perth Basin, where you've got up to 1,500 metres of sediments there. So two very different types of parent material for the soils. In the wheat belt, it's not just igneous rocks. You've got sediments in the valleys, so those big broad wheat belt valleys. You've got sediments in places like the Collie Basin and Collie, and along the south coast, from Esperance right across to probably, I think, about Northcliffe, you've got very shallow, not very shallow, they can be 100 metres deep or more, sediments on top of the igneous rocks, and they're called the plantagenet beds, and they bring with them some features. So if you're on the south coast, you'll know that a lot of the soils are very, the sands are very fine textured, very fine grained, and one of the reasons for that is those plantagenet beds were, the sediments sort of came in, and apparently there's quite a large lagoon, and you have the fine grained sediments settled out, along with sponges and other things that you can see in that part of the world. But the Yilgarn, very old rocks, mainly granites and gneisses, but as we'll see, there are some more subtleties and different geologies in there as well. So broad regional context, and then we'll delve into it. So we talk about geomorphology. Geomorphology is basically describing the shape of the landscape, so morphology, and then we talk about geomorphic processes, which are the things that drive changes. So things like erosion caused by water or by wind and deposition. So a lot of the work, and you'll see a lot of reports from the region, they really talk about these four major zones or regions. And so you've got the zone of ancient drainage. So that's basically east of Meckering and north of Pingerup. The inland areas with broad valleys, valley floors, not a lot of relief in the landscape, maybe 20, 30, 40 metres total relief in the landscape. That's the old, I guess, sort of intact landscape of this very old region. Next, you can see what's termed the zone of rejuvenated drainage. And what's happened there is that both because the land is uplifted and also sea level has dropped, is the rivers such as the Avon, the Blackwood, and the others have cut down into the landscape, and it's rejuvenated. You can see streamlines. There's much more relief in the landscape. So if you go to a place like York or Bridgetown, you'll know that you've got 80, 100 metres, maybe 150 metres of relief or distance between the tops of the hills and the valley floor. And that's had big impacts on the pattern of soils, as we'll see as we go on. Then you've got the Darling Range, and you'll be familiar with that. And again, that's relatively not a lot of relief in the Darling Range, broader valleys, particularly at the headwaters of the westerly flowing rivers, and the fourth broad zone's the Swan Coastal Plain. And so what I'll attempt to do, visitors, is sort of just go through those zones with a bit of mixing and matching, but try and present a coherent idea of what's going on. This is from the work that Maurice Mulcahy did in the 1960s, very broad map of the soils of the region. And you can see those zones I just talked about. So the zone of ancient drainage, you can see the drainage lines, the Swan Avon river goes way back to, I think, Lake King and Lake Grace. There's Lake Grace there. So you can see there's very old drainage lines. The zone of rejuvenated drainage, which is through here. And there's also one on the south coast where the rivers have cut down into the landscape and produce more relief and fresher soils along the valleys. So if you're on the south coast, you'll know there's some quite fertile soils near Ravensthorpe and Jerramungup. And there's sort of fertile soils, obviously, through the York, northern 2J region as a result of the rivers cutting down into the landscape. You've got the Darling Range and then the Swan Coastal Plain in all its glory. Are there any questions up to now?
Richard, is that information available somewhere for the participants to sort of to look at a later date or in further depth? Are there soil classification information available for those different soil zones?
Probably the best thing, there's a book, and Richard will tell us if it's still available. It's called The Reference Soils of Western Australia, and it was done by the Ag Department and the Soil Science Society of Australia, written by Bill MacArthur back in the, I think it was 91, there's a second edition. And that's quite a nice story. It's got probably not the best title, but in there he describes the different regions and the pattern and probably pretty much what I just said, but for different regions he went to bush sites and got what he thought were good representative soils and also presented some data. There's a lot of soil bulletins, which are probably a bit impenetrable. And I don't know whether they're all available. So the Ag Department's pretty much mapped the soils across the region over the last 30 odd years. And there's sort of various CSIRO reports, but a lot of those are, they're not readily available. But the reference soils books, the best example, Richard will be able to tell you if he's still online.
This one or a different one?
Beg your pardon?
Is there another one?
That's another one. That's based on classification. So the Ag Department, when they finished all the soil mapping, they came up with the classification of the soils. And I think it's got about 60 soil. They reckon, well, you've got the book there.
Yeah, this one's got a lot. Yeah,
it's about 60 different soils, and they describe the uses and what have you. But to tell you the truth, I find that stuff quite impenetrable. You know, if you're working in an area, you probably use it, and you know, it's a good framework, but it's not sort of bedtime reading where you're, you know, sort of well, some of you might, but certainly not what I'd consider bedtime reading.
Yeah, I do have some in my office, some copies of the reference soils book. I was just quickly checking if I've got a PDF copy of it. Yeah, it's still around, and I agree that chapter in MacArthur is probably the best sort of simple synthesis that I've seen that pulls together all of those concepts that you're talking about.
Yeah, he writes well, and basically he wrote it after sort of 50 years of charging around the landscape, digging holes by hand, and you know, keen observation. And he also brings in land use, because that's the reason why CSIRO commissioned that work, was because they're interested in you know, uses of the soils. But he also brings in the natural vegetation, because the natural vegetation follows the soil pattern incredibly well. But I guess that's a discussion for another day.
There's one thing I would say, Richard, in addition, is that a lot of that work was done in the central wheat belt. And I think you can extrapolate it out, but the further away from there you go, the more variations on that theme you're likely to see. So I'm thinking, for example, of north of Geraldton, Chapman Valley up into Northampton and beyond. It's a long way from the central wheat belt, and so there's probably some variations there that are not well described in that sort of literature.
Yeah, and also you can see it with the map is, I don't know whether it was deliberate, but they didn't go there. But anyway, so we've got that. So the soils depend a lot on the underlying geology. And so in the Yilgarn, so that's the granitic-based material that's to the east of the Darling Scarp, you've got granites, gneisses, dolerites, and obviously you've got other minerals. That's the WA mining industry, or some of it. But then within the different rock types, you've got different minerals. So granite, for example, is quartz, feldspar, and mica. But what happens is each of those minerals breaks down or weathers differently. So quartz is quite resistant, or very, very resistant. And so if you weather or the rocks break down over millions of years, quartz tends to stay in the landscape, whereas other minerals like the feldspars, so there's orthoclays, plagioclays, and the micas break down, and they break down into clay, such as kaolin clay, which a lot of you would be familiar with. You see it in a lot of the road cuttings and farm dams, and iron and aluminium oxides, which, and we'll come to that in a bit more detail. Gneiss is the same. Dolerites, so through the region you've got dikes or strips of different material that have been injected into the granitic bedrock. We often talk about dolerite dikes, and you can see them at seeding time, sort of areas of reddy brown soil across paddocks, and they've got a different mineral composition, and those minerals break down. Well, they break down as well, but they have different endpoints, not a lot of quartz in them. So they're examples of there's granite and dolerite, different minerals. But a key feature of the region is all the rocks, and doesn't matter if it's a sedimentary infills like we had in the valleys, South Coast, Collie Basin, Perth Basin even, so as you go up towards Dandaragan, Mininu, places like that, the sedimentary rocks, they're all weathered under what we think were tropical conditions 30 or 40 million years ago. And so if you go to tropical environments elsewhere in the world, like Thailand or Brazil, you've got warm conditions, a lot of water, and under those conditions, rocks break down, the minerals break down, and you end up with soils which are many meters deep. And that's what we've got across a large part of the southwest is what we call deep weathering profiles or laterite profiles, sort of various terms for them. Here's a road cutting on the just near Sawyers Valley, and this gentleman was an Italian soil scientist who'd read about these laterite or deep weathering profiles and never actually seen them, and it was pouring with rain, and I just stopped on the side of the road, and he was like a rabbit out of the car, and he was we couldn't get him down. He was so excited, and he went to the Northern Post Office with about 15 kilograms of rock samples, and I think it was an interesting day. But the basic point is you can see a forest, but you can see a very the deep weathering profiles, and those profiles can be up to 100 meters, deep, and they form over diverse geologies. So the upshot of that weathering is you end up with, this is generalising, you end up with a sequence of soil horizons which are pretty consistent. So the upper layers are sandy with the predominance of quartz. You end up with iron or aluminium gravels. So that's ironstone gravels, common term, where there's a lot of aluminium. That's the stuff that's mined for bauxite. So it's an accumulation of iron and aluminium near the surface in those very characteristic gravelly soils. You end up with a mottled zone where you've got a staining of iron and aluminium. That's probably what we can see there. And then if you go deeper, you end up with the white clays or kaolin clays, which are very common. So you see them in farm dams, you see them in a lot of road cuttings. So it's just predominantly kaolin clay with quartz, but also maybe small amounts of iron and aluminium oxides, and they're the characteristic colours, the yellow-brown colours that sort of, I guess, the classic colours of soils of inland Australia. If you go deeper, you can have weathered rock, so you can still see the fabric of the rock with weathered crystals of feldspars and quartz. And then if you go deeper, you have the bedrock. So that's sort of a pretty classic view, but of the what's happened, tropical weathering, and that weathering occurred right across the region. In fact, went right across much of southern Australia. So that's the base profile, if you like, and I won't delve into that much more, but and so you can see this is a mine in I think it's Boddington, and you can see the weathering profile there is to many meters deep. But the deep weathering also explains salinity, which is probably counterintuitive because you're saying, well, weathering removes things that dissolve. They get carried out of the landscape. But in this region, because we're dealing with long periods of time, is the last 100,000, 200,000 years have been quite dry. And those deep weathering profiles have accumulated salt. So salt's being carried inland from the coast in rainfall, probably very small amounts each year. And it hasn't leached out of the landscape, it's accumulated in the landscape. And so you end up with large stores of salt in the weathering profiles, maybe 10 to 15,000 tonnes per hectare, according to some calculations. And with salinity is basically what happens is you disrupt the water balance through land clearing. So you're replacing deep-rooted plants that use most of the water with shallow-rooted plants. And so water starts moving through the landscape, dissolving salt and making an appearance in lower landscape positions. But the reason we do have salinity in the landscape is because of that prior deep weathering. So where you don't have deep weathering profiles, you don't have a lot of salt, you might have some, but the predominance is where you've got those salt stores in the landscape. And here's some images from Wickerton, with a site we've been working on since 2001 with our carbon forestry project. But what was a valley paddock, which was pretty productive in the early 1960s, has become a classic salt scald down there. But the other endpoint of millions of years of weathering is quartz, as I mentioned, is quite resistant, or very resistant. So it accumulates in the landscape, and some has been transported away, and lots ended up on the in the Perth Basin, and it explains why we've got a lot of very sandy soils in Perth, for example, and I'll come back to that later. But you also have redistribution within the landscape. So you've got the sandplain soils, which are very common in the central wheat belt, for example. You've got the sandplains, northern sandplain, inland of west of, say, places like Three Springs and Carnamo, and there you've had sediments. So west of Three Springs, you're in the Perth Basin. So you've had sediments being transported in the past. They've been weathered, and you've got the accumulation of more sand in those areas. And then also spillways, again, a pretty classic thing in the wheat belt, where you can have gravelly rises, but spillways or lower landscape positions which are got deposits of sand. The next thing that happened is sea levels have risen and fallen over time. The Australian continent's been uplifted. And as a result of that, the drainage is what we term rejuvenated, or made active, has been made active again. And so what was probably similar to the central wheat belt, with these very broad flat valleys full of a lot of sediments, not a lot of relief in the landscape, which we can see in the image here, over here, with the deep weathering profile across the whole landscape, is what's happened in the zone of rejuvenated drainage is the drainage lines have cut down into that old landscape, and some of the soils in the valleys have formed on the underlying rock. And so that's what you see in places like York and Bridgetown and Jerramungup, east of Jerramungup, on the Gardner River, where in the valleys you've got some reasonably fertile soils. You know, they're not fantastically fertile because they're formed from granites, but they're relatively young and fertile. Whereas in the upland areas, you've got remnants of the old deep weathering profile. And depending on where you are, you might have different degrees of cutting back of that profile. So some parts of the wheat belt, you'd be familiar with breakaways, where you've got these residual areas with gravelly material on top, and very classic scarp faces. So you see them through places like Pingelly and right down to the south coast. In other areas, those gravelly horizons have been taken away, and a lot of the soils have formed on what was the pallid zone. So that's what you see through Narrogin, Kojonup, up through New Norcia, where the parent materials of the soils are quite often the pallid zone clays rather than the gravels. There might be some residual gravels in higher parts of the landscape, but not a lot. So the pattern of current pattern of soils is very much controlled by, firstly, this deep weathering, which resulted in that sequence of horizons, and then the local effects of the drainage lines. So you can end up with very young, fresh soils. You can end up with old, gravelly and sandy soils. Are there any questions about that? That's okay, we'll keep going. And there's various studies, and this is obviously also of interest to the miners, because they're trying to explore for the minerals like gold and nickel and what have you in this very old, deeply weathered landscape. So they've put a lot of effort into understanding what's going on in the landscape. So back to that very broad map of the soil map of the southwest. So you can see the old ancient drainage with drainage lines and a lot of flat relief, and then this zone of rejuvenated drainage where those soils have been, quite fresh young soils have formed along the river valleys. And here's some examples. We're looking at dead blue gums in this example, and not surprisingly, because it doesn't rain here for 6 months of the year, if you plant blue gums on soils which are only 1/2 metre deep over bedrock or saprolite, they die. And so we found quite rapidly that you needed to look for soils which still had intact deep weathering profiles for those trees to survive. They don't grow as fast because those soils aren't as fertile because they've been weathered, but you've got the water storage capacity for them to survive over summer. And the deep weathering profile, if you're interested in the local flora of the region, the deep weathering profile is the reason we've got the Jarrah forest, for example, because it doesn't rain for several months of the year. And if we had the shallow soils, which are 20, 30 centimetres deep over bedrock, you wouldn't have the storage capacity in those soils to carry the forests over summer. And again, if you look at some of the native forests through the region, you'll see the density of biomass in the valleys where you've got rock outcrops is always much less than in the upland areas where you've got the deep weathering profiles. So a bit of detail there. So the sand in the landscape's been retained, and so a feature of large areas of the wheat belt are what we term sand plains, where you've just got this accumulation of quartz sand. Might be a few centimetres deep, it might be metres deep, but it's basically what probably half the farms in the wheat belt are dealing with. A very common soil in this part of the region is what are called duplex soils, or sand over clay soils, or texture contrast soils. And again, they're very widespread, and there's an example on the right from Jerramunga. And basically you've got sand overlying clay. That sand horizon is developed in different ways. So in some places it's because of deposition. So you've had wind in the past, carried sand and deposited it somewhere else. Commonly you get sandy soils at the bottom or the break of slopes because it's eroded and been carried down slope. But in other cases, that sand horizon's developed in place, and just as the clay in the material, it just under the influence of long periods of time and water, it moves down through the profile and accumulates at the interface of the sand and clay horizon. So here you've got a sandy surface. I think it's about 20 centimetres deep there, and then clay at depth. And those soils do cause some challenges in under the climate of a few years ago. They were very prone to waterlogging because the water could penetrate the sandy horizons quite readily, but not penetrate the subsoil clays. Some of the soils stop penetration of roots of annual plants because of their bulk density, the density of that subsoil. Sometimes they can be quite alkaline or quite acid as well, which stops the penetration of roots. You might ask what's happening in the valley floors out in the wheat belt, and there's actually quite a lot. And again, understanding what processes are occurring can explain some of the soil properties. So this was taken a few years ago when we could fly around. It's out in the up near the rabbit-proof fence, with a very classic wheat belt view of these broad drainage lines. So these are old, what we term paleo drainage lines. It's part of the Swan-Avon system, all clogged up with sediments, but you have these salt lakes have formed in those areas. So they're a natural feature of the landscape. You know, we're dealing with salinity in the landscape now, but salinity is also a natural feature of this landscape. So the salts that have leached out of the upland areas, they accumulate in the valley floors, and you end up with brines, hypersaline. You know, they're very, very saline, nothing can grow, and you have these salt lakes have formed in those areas. And they're quite often associated with what are called lunettes. So if you drive out of places like Lake Grace, Wagen, Lake King, a very, very distinctive feature with salt lakes are dunes that occur on the southeastern side. They've been blown out of the salt lakes, again under previous probably more arid climate, and they're very characteristic. They're dunes, but in a lot of cases they're not sand, they're clay. So if you stop at the road cuttings in some of those places like Lake King, you'll see that those lunettes can be quite clayey. And it's basically what's happened is that clay pellets have eroded from the salt lakes and been deposited on the lake shore. This is stuff we did down at Jerramungup years ago, and we surveyed cross sections going out several metres or kilometres from 2 or 3 of the salt lakes, and you can see a very distinctive pattern of these old source bordering dunes occupying the valley floors. It's one case of going out 5 kilometres from the present boundary, and so they've got different materials. And I won't get out of that one there, but that pattern and this process of solid material dissolving, moving into the valley floors, forming brines. It's not just salt. You can have sodium chloride, you can have potassium, magnesium, calcium. In inland areas, you can have uranium. Whatever the basement rock is of the landscape, these solutions move down into the solutions form in the valleys, and in a lot of cases they can be quite alkaline or can have quite high pHs. And because you've got or had periods of dry, dusty conditions forming the dunes, you've also had clouds of quite alkaline or limey material dusting the landscape. So in this little graph here, you can see we've measured the silt content, very fine material with distance from a salt lake, and you can see that that decreases with distance. but calcium carbonate or lime content also varies. So near the salt lake, you can have deposits of lime or calcrete in the dunes, but you also have a dusting of that material downwind of the salt lakes. And a common observation is that the upland areas, they're quite often alkaline. They can have alkaline subsoils, and whether they're alkaline or acidic, I think depends on whether there's a salt lake upwind. So if you've got a big salt lake, you can imagine it emitting large amounts of this limey material over time, and so you can quite often find nodules of lime at depth downwind of these salt lakes, many kilometres distant, and that's sort of a feature of the zone of ancient drainage. So just recap. So we've had weathering, which is basically the original rocks and minerals being disintegrating, dissolving, breaking down by physical and chemical and obviously biological processes over very long periods of time, and more than likely under previous climates, so the tropical climates that I mentioned earlier. You need this weathering to loosen up materials. So you can imagine a bit of granite, not a lot of material is going to slough off it, but if you weather that granite and break down the materials, that material can be transported. And so you've got these weathered profiles in the landscape really being the key to a lot of soil properties in the across large areas of the agricultural landscape. And one of the keys to understanding that is the laterite or deep weathering profile and what's happened to it afterwards. So have the local river systems cut down into the landscape? Have they stripped away that old weathered material? Has it all gone? Has it only partly gone? Because it's obviously a work in process. And that explains the properties of many of the current soils, and also the pattern of water storage in the landscape, salinity, natural vegetation, and the patterns of soil fertility. And so that's sort of recapping that again. People quite often ask, wave rock, and you're all familiar with that, is that a wind-blown feature? And the answer is no. There hasn't been sort of howling winds out there sort of cutting away and taking out the bottom slope. These are features that occur in several parts of the world where they were previously buried at depth within the weathering profile. The weathering profile has been removed, and this is the resistant material. And yeah. Okay, so that finishes the Yilgarn and the wheat belt. Are there any questions at all? Okay, we'll continue. So a quick so we go back to the broad geology. Now we'll have a quick look at the Perth Basin. And the Perth Basin heads all the way, was basically from the south coast. You can see it down here, past Perth and up to Mininu, maybe Dongara, well, obviously Dongara, and as Richard mentioned, sort of get a little bit hazy as you head north of Geraldton, but nonetheless, it's major feature of this part of the world. And there's been obviously fluctuating sea levels over the last 18, 20,000 years. So things like rock nests were previously attached to the land and the islands off the coast. And there's evidence from the, I guess, sort of sonar surveys off the coast that the Swan Avon system has been in place for many millennia. So this image shows the, I guess, the elevation of the seabed, and on the left it becomes very deep very quickly, and you can see the coastline there. But the Swan Avon system is cut into the coastal zone to a depth of many metres, which indicates that the Swan Avon system in the past was probably a very active river system. But we're dealing with literally billions of years of history here. So this is predominantly based on the area around Perth, but if we look at the soils and landforms around Perth, there's a very consistent pattern. So close to the coast, you've got dunes, which have got quite a lot of lime in them. You go inland, you've got more subdued dunes. They're the Bassendean sands. You've got alluvial soils associated with the rivers coming out of the scarp, some sediments on the side of the Darling Range, and then if you go further up into the hills, you're back into that deeply weathered terrain that we've just covered. So it's sort of a pretty classic diagram of the region, and a very distinctive soil pattern as you run along that sequence from the coast, with quite young soils which contain greater fertility, through to some pretty worn out old soils on the Bassendean dunes. So that's the geology, and just some images of some of the materials. So some of the soils on the coast can be quite shallow with limestone, and this is where the most of the lime deposits come from. The coastal zone right up to Dongara and beyond. As you go further inland, the sands become more developed. There's a sand pit there. You can see some bedding, and then as you go further inland, you can see the soils on the edge of the scarp. And there's been quite a lot of work obviously done on these dunes. Here's another view. This was based on a work on the ecology, vegetation, and from close to the coast through to the very old dunes. And these authors attempted to put some ages on the different dunes. So they're suggesting some of the soils, Bassendean soils, which are those very white sands which you see on the eastern edge of the Swan Coastal Plain, could be up to 2 million years or more old. And as the deep weathering profile is important for explaining salinity, this pattern's important for explaining groundwater resources. And the southwest, probably half, maybe more of the water now comes from the ground, and not just in Perth, but through the southwest as well. And basically those sediments of the Perth Basin, you can have clay sediments, you can have sandy and gravelly sediments. The sandy and gravelly sediments can contain water, groundwater. So it's what's termed aquifers. And here's a very schematic view, if you like, showing the Gnangara Mound, which is just north of Perth, but the same principle applies in the sediments elsewhere, where the sands are containing water, and that sand can be extracted for human use. And so again, you have a pretty classic pattern of upland areas are sandy, and then the interjunal areas or swales can contain wetlands, and that's sort of a pretty common pattern through the Perth Basin. So the formation of the soils, basically you have enough time, add water, warmer conditions, and things break down, things move through the soil, things dissolve, accumulate at depth, erosion, deposition, a few processes, and that's how the soils of the Swan Coastal Plain formed. Now, just thinking about how you can use some of this information, and it'll probably be another 15 minutes if you're wondering about a coffee break. If you look at that map that I've shown a few times of the region, I think it's very useful for explaining, sort of this sort of broad story about how different materials and soils got where they are, and it's a good framework for describing that. But if you're interested in managing a specific farm, it's not very useful at all. So we need to drill down and think of the soil pattern at the farm level. And so this is 10,000 hectares near Jerramungup, where years ago, I think I took about 1,600 holes by hand and came up with a reasonable idea of the soil pattern. But you can see even in that relatively small area, they're quite distinct soils. In that case, we thought we'd found about 17, which will respond to different aspects of management differently. It's expensive for people to charge around the landscape, digging a lot of holes for high value horticulture and some land uses that can be justified, but for broad acres, broad acre farming, it's probably not. So there's a range of new technologies that some of you would be familiar with. So things like gamma radiometrics, EM in various shapes and forms that can give you, combined with topographic information, can show a pattern of different soil materials in the landscape. And the trick is to relate those different patterns to things that we're interested in. And that's where Maria's going to come in the next 2 or 3 years with her thesis, looking how we can use this type of information for predicting where soil water repellency is going to be a problem, or where it's likely to develop into a problem. So as an example, stuff I did with Mike Wong when he was with CSIRO years ago, we looked at gamma radiometrics. So this is something that can be measured across farms, and I know that several consultants are doing this, and we were interested in whether that could provide information about things we were interested in. So things like potassium supply to crops, that's down the bottom, and it, in a broad sense, it could delineate areas where potassium might develop into, potassium deficiency might develop into being an issue, or where it was highly unlikely. And so that was useful. The likelihood of wind erosion. So wind erosion is related to soil clay content. So the more clay you've got in soils, the less likely they are to erode. unless management's really adventurous. So you can see here on the top left that the gamma potassium count from radiometrics gave a good indication of soil clay content, where it was clay, where it wasn't. And that could be related to the likelihood of wind erosion. So soils with very low potassium counts, highly susceptible, higher counts. There was data there, well, there's data across the whole range. There was no wind erosion on those more potassium-rich soils, which could be delineated by gamma K. And then with non-wetting, you can see that the non-wetting soil water repellency was predominantly occurring on soils with very low gamma counts. And again, that suggests that that sort of information that's been produced can be used to develop indications of how to change management. So what factors, soil factors, drive plant production? So you've got available water, and that comes from rainfall, amount of evaporation in an area, in some areas irrigation, amount of radiation from sunlight, and that affects both photosynthesis and also the temperature, so warm conditions, cold conditions, and then a range of soil properties, so things that affect crop nutrition, plant nutrition, things that hold water holding capacity. So sandy soils tend to be very well drained, not hold a lot of moisture, water. After it rains, you can have leaching, whereas more clay or loamy soils hold water better. And then for some crops, soils also provide stability. So for planting trees, you don't want them to blow down. And some soils with plantations and orchards, they don't provide a lot of stability to the crops, probably less of an issue in the wheat belt. But then other properties like salinity, waterlogging, acidity, and alkalinity can affect the growth of plants. And we want to manage those issues. The main components of soils is when we take soils in the laboratory, we break them down and we measure the amount of fine material or clay, the amount of coarse material, that's fine and coarse sand, and the amount of organic matter. And the combination of those particles produces what are termed soil texture classes, which some of you will be familiar with. So we quite often talk about sands, but if you've got more clay add clay to a sandy soil, you can have a sandy loam. If there's not a lot of sand, you can have what's termed a clay, and there's a whole range of names that people use for different texture classes. If we'd done the field component of this, we'd show you how to assess the soil texture in the field with the what's termed the ribbon technique, where you work the soil up and you can make a pretty accurate assessment of the proportions of the different soil particles that are present. Those particles can have different compositions. So the clay size material can be comprised of quite different minerals. So I've mentioned kaolin clay, which comes out of deep weathering. In other parts of the world, the clay minerals can be things like illite and smectite, which are much, much more fertile. So some of the world's richest soils, the alluvial plains of the Nile and the Mississippi and Northern Europe, a lot of those contain these smectite clays, which are much more fertile than kaolin. In this part of the world, there's a lot of iron and aluminium oxides, and then the feldspars and quartz that we mentioned earlier on. So I think it's a bit of a repeat in terms of how soils contribute to plant production and quality. But probably the key takeaway from this is when you're thinking about soils, quite often people just think about what's on the surface because it's readily accessible. But it's always useful to think about soil as a three-dimensional entity across the landscape. Think about the top metre. If you're farming with annual crops and pastures, if you're farming trees, think about the top 5 or 10 metres, because what happens below the surface can have an enormous impact, because that's basically where the plant roots go. Another important feature I think is worth drawing out is that although we quite often think of West Australian soils, many of them as being sandy, and they are, not all of them, small amounts of clay in sandy soils can have a huge influence on a range of properties. So we've seen how they can affect wind erosion, water repellency, even trafficability, driving across paddocks. So if you've got a soil that's got no sand at all, it might be a white sandy soil, you can get bogged relatively easily because there's no bearing capacity. Add 2 or 3% clay to those soils and a lot of things change. You know, crop yields, stability, less water repellency, less wind erosion, and what have you. And that's really the basis why people have started applying clay to sandy soils and getting some of the results that they have got, not only in overcoming water repellency, but in improving the general performance of those sandy soils. How can soils constrain plant production? So we've covered some of these, waterlogging, salinity, nutrient deficiencies, the list's there, and these are the things that people are attempting to manage, but there are common management responses. So waterlogging, you have drainage. Salinity, sometimes drainage, sometimes whole landscape water management. Nutrient deficiencies in the soils because of that weathering and what's happened over that long geologic period. A lot of West Australian soils are or have been exceedingly nutrient deficient. You apply fertilisers. Extremes of pH, apply lime. Alkalinity, not sure if there are any broad scale treatments. Toxicities such as boron, you can change the crop variety. Hard setting soils, they can occur in valleys. Apply gypsum and rip. Non-wetting, apply clay, and compaction, ripping. And that's been one of the, I guess, success stories of the last 20 odd years with, sort of pulses of people sort of ripping soils to more than 10 centimetres deep across large areas. But probably the key thing is all these different management inputs and requirements, because they vary with soil properties, is you need to have a handle on the soil pattern to apply them most, strategically. Okay, last slide. So just recapping again. So the nature of the soil landscapes, the pattern and properties, you can explain a lot of what's there now by what's happened in the past, by the geology, landscape processes, and I think it provides a reasonable framework. Won't be absolutely accurate in every area, but I think it's a pretty reasonable model to explain what's going on. So you've had deep weathering, you've had this accumulation of quartz in many soils with their problems, both around water and fertility, but probably ending up in a high point. I think the farming in the last years, like you look at a lot of land care literature and the soil strategy, national soil strategy that's coming out in a few weeks, is quite often it sort of presents quite a pessimistic view about problems. But I think we can sort of end by saying that Western Australian farming has succeeded in a difficult environment with quite profitable systems. Okay, thanks. I'll finish there.
Thanks, Richard. That was fantastic and yeah, really comprehensive. So I really appreciate that. And we have some questions in the chat box. And if anyone's got any other questions, feel free to add them to the chat box. Freya's got a couple of questions. Freya, are you happy to unmute yourself and ask those questions if you like?
Yep, okay.
There might be a little bit of noise in the background just because I'm in the open office at the moment.
Okay.
I don't know if this is a really embarrassing statement to say, Richard, but I did hear, I cannot remember who said it, but that, yeah, as sandy soils have an ability to allow water to infiltrate to a deeper level, that during a drying climate, we might see clays sort of dry out much quicker. And the sandy soils in a crop, like in an agricultural sort of context, might start performing slightly, like comparatively better than they do now when you look at them against more clay-rich soils. Is that total BS?
I think so. I guess you guys be close to the ground, because I think that's what people say about dry years too, isn't it? You know, like people notice difference in crops between you know, yields between dry years and dry finishes and wetter years, and that'd be a common observation from, because climate change, if it's going to be drier, is we've probably got analogues during our current system. You know, so you get a year with a couple hundred mils of rain. Maybe that's going to be what happens in the future. But yeah, I guess during the dry years, you get clues about what it's going to be like under future climates. Yeah, but it sounds reasonable.
And just my second question was, for us where we are in Cranbrook and Tambela, we yeah, sort of sandy soils with all their issues is a key thing that gets brought up that our grower group is asked to address and continue to work on. And it seems like from most of the stuff that we hear and some of the presentations we've had through this so far, that incorporating clay through whatever means seems to be the best option for a lot of farmers. And I understand the expense is huge, but I'm just wondering if incorporating more clay into your sandy soil profile has the ability to increase your production, but also all the other benefits to your soils with carbon and all those sorts of things. Why have I missed it, or why there isn't just more of a coordinated effort to get this happening at a really large scale? Because it seems like most people still can't afford it and will not be able to afford to do it, from what I hear.
Yeah, I think well, Richard's done work with the Ag Department on at Esperance on long-term claying trials. We've done some work on the south of Perth on stuff where Alcoa added clay to sandy soils, and yeah, it increases the soil carbon content. And we've had a bit of a push to try and get interest in getting carbon credits for that, and I think that's been incorporated into the new methodology. I don't think you'd make a massive money. Like we were looking at 1 or 2 tonnes of carbon per hectare per year, CO2, and I think the carbon price is $17. So that's $30 or $40 a year return. And the stuff we looked at, it looked like it was sort of a break-even proposition with the cost of transport and spreading, but you're getting the other benefits with crop yield and overcoming non-wetting and in areas where there are estuaries, stopping leaching of nutrients or losing nitrogen and phosphorus into the groundwater. So yeah, I think it's worth pursuing, but it's going to depend on the economics. But apparently, it's been quite a large uptake in Esperance.
So would you suggest then, because we've got some stuff happening in terms of like above ground carbon, like growing trees and things like that. Would you suggest that if we're trying to get people to prioritise adding more clay into their sandy soils, looking into, because I'm not super experienced with the methodology behind soil carbon and carbon credits, but do you think that that's sort of a positive way to get people doing more of it then, is trying to offer that, even though you said it's not a super large payment opportunity, but
I think you need a longer discussion, because carbon is going to, soil carbon's made a reappearance with the federal government, and I think they're going to be pushing it pretty heavily going forward, to meet the 2050 targets. I think, and there's a methodology, but you'd have to look at the site-by-site situation, rather than sort of say to farmers, well, this is a good thing, do it. You actually work out whether it's economic and working. So yeah, I'd treat it with a little bit of care, and I'd put it in the potentially useful category rather than do it next week. But Richard might have some comments about down at Esperance, but there's been some pretty enthusiastic application of clays on the Esperance sand plain.
Yeah, look, I'm happy to elaborate. There's been a couple of long-term experiments down at Esperance, one that ran for about 15 years, another that's at about 10 or 11 years. And so the clays that they've added, they're getting on average 50% yield increases, but it's taking sort of 5 to 7 years before you get to break even and start to make a profit from that, because the initial investment is up to $1,000 per hectare. So it's, it's a big investment, and but the payoff in the long term is pretty good, and it does seem to be a benefit that's going to persist for a long time once you've added the clay. There's probably about over 100,000 hectares of land that's been treated by farmers with clay. And usually it's just the local clay within the paddock, dig it up, spread it, mix it in. And that's going to be the cheapest clay. And over time, people have worked out the ways to do that and the ways not to do it. So if you dig up the clay and just leave it on the surface with very little mixing or incorporation, you might end up in a worse situation. Similar to what you were talking about before, the clay at the surface just soaks up all the water, and you get very poor depth penetration of rainfall, especially on light rainfall events. And not all clays are the same. So some of the clays on the south coast are really loaded with potassium. Further north, they don't contain much potassium as well. In addition to building carbon, you're also in those clayed soils holding on to more phosphorus, building sulfur. Some of the clays have got a little bit of alkalinity, so there's a pH benefit. So if you want to increase the clay percentage by 1% in the top 30 centimetres, you're talking about 40 tonnes of actual clay per hectare. And most subsoils would contain, let's say, 30% clay. So you multiply that by 3.5. So you're looking at a minimum of 120, 150 tonnes per hectare to increase it by 1%. And it doesn't seem to be worthwhile to go more than about 5 or 6% clay. And we're currently doing research for the soil CRC where we're looking at some novel clay and compost mixes to see if you can get similar benefits with much smaller amounts of those materials. But yeah, look, I think there's probably enough evidence already that DPIRD could probably come up with a best practice guidelines. And if the government had the mind to invest big in trying to overcome the limitations on productivity of these large areas of sands, that it's, it probably would be a feasible way of doing that.
It just seems that, yeah, soil health, the thing that a lot of people really are starting to care about, but also we need to produce, food, and predictions are that there'll be, shortages in the long term. So it seems like claying is, quite a well accepted solution within the farming community. So it'd be cool to see more of it happening. We had it with frost this year. We got completely frosted, and the only bits that we delved were comparatively from 0 tonne to about 3.5 tonne. So yeah, it was pretty impressive. So no, anyway, I've monopolized a heap of time, so thank you so much, guys. Other questions get answered.
I think there is a caveat, because the way you can get clay into soil is some people do it with borrow pits, and, dig and spread, but others do delving, where you bring clay up from the subsoil, and I have seen examples where people have delved and they brought up some pretty murky subsoils, which sometimes you get domed subsoils, so you end up with sort of large domes sort of scattered across paddocks and whatever. So that's sort of part of the evaluation as well, as make sure you don't create problems there. And I know during the ripping craze that particularly in the northern sandplain, there'd been some pretty spectacular results. I saw some stuff down at Lake Grace where people had sort of ripped away, and they weren't so impressed because they had sort of these pretty crappy clay subsoils. So it's probably test strip territory in some areas rather than broad, sort of delving in and not jumping in.
Is pun not intended? Is there like a not a cheat sheet but a guidance note on what can be done? The assessment for soils that are suitable for delving, claying.
There's a really good one that GRDC did. I'll find it. I found it really just it's very general, but it's quite, if someone had no idea, it's quite helpful, and the tests that should be done and things that you can do and things that you'll need to get tested for. And so I remember, Richard, you said that, yes, saline clay and things like that can be a major issue in our areas. So we did a little tutorial at our last committee meeting on what you need to look at for that stuff. So yeah.
Yeah, great. And it's just those issues like Richard was mentioning about boron, bringing that to the sort of, top 10 centimetres rooting zone is a bit of a risk.
Make bricks. I was just wondering whether it's worth just ripping through we've only got 1 minute anyway. Some questions. I think you had a question, Andy, about is loam a combination of sand and silt? Yes, it is. Yeah, so basically with those texture triangles, we sort of think about sand, silt and clay and the combination of them, and loam's one of the categories that comes out of that. And I think the other thing is, you probably got a sense from the talk, is, you know, a lot of people have been working with soils and farming whatever over the years, and there's a lot of terminology that's pretty mixed up, you know. And the Australian government years ago, they tried to standardise, you know, the description of soils and you know, soil classification and what have you, but not always to a great success. But that's just the nature of the beast. So we've got that. What is a small amount of clay in tonnes per hectare? How do you address increased pH after long-term irrigation? Probably leaching, is it? Or I suppose you can't, because that's sort of more irrigation, isn't it? I think dealing with alkaline conditions is a problem in soil conditions. You know, if you want to treat it over broad areas, I don't know whether Richard's got any views, but if you had an irrigation paddock where you know, it's sort of become quite alkaline, obviously you can't use more water, irrigation water, to leach it. There's maybe it's letting it lie fallow and assume that it's going to recover. I don't know. Do you have any ideas, Richard?
Yeah, I guess it depends on the quality of the irrigation water, but and the alkaline salts. But if the alkalinity results in calcium carbonate formation, then the pH will probably end up buffering itself at somewhere between about 7.5 and 8 pH, which is high for many plants. The only way that I could think of, and it would depend on the cropping or farming system, whether that would work, is ammonium sulfate is an acidifying nitrogen fertilizer. So in that situation, you might switch over from urea or other nitrogen fertilizers to ammonium sulfate, and you get some acidification reaction from that, which would help to offset or partially reverse the alkali reaction from the irrigation water.
Is DAP, diammonium phosphate, is that also more acidifying, say, compared to MAP, or?
It is, well, it's about the amount of ammonia that you add. So yes, you would normally add more ammonium nitrogen as DAP, and therefore more acidifying.
One approach would be deep cultivation. You know, if the alkalinity just accumulated near the surface, it may be cultivate to dilute and you know, sort of turn it over, particularly if it's a horticultural situation. You know, you might be able to justify the expense there.
There's also quite big differences between plant species and their tolerance to alkalinity. So you might be forced into a situation where you had to drop out some crops and switch to others.
Yeah.
And you just had a question about the difference between kaolin clay and bentonite clay.
Do you want me to answer that?
Yeah, sure.
Yeah, look, there are many different classes of clay, and kaolinite, which is our number one and most prevalent clay, is what's called a low activity clay. So it does have quite good surface area compared to sand and silt, but it doesn't have the same reactivity as a bentonite clay, which for the same weight has a much, much higher surface area and charge, and therefore it's much more reactive, holding water and nutrients. And we do have some bentonite mines in Western Australia, and you can buy it for home gardens. We're actually going to probably include it in a trial that we set up with the West Midlands group this year, looking at a range of different soil amendments for sands to see if we can increase the retention of water and nutrients. And I know DPIRD did a little bit of work on bentonite additions to coastal sands to improve them for vegetable or horticultural production. And Andy, I think your company uses some bentonite additives in some of the composts as well. So,
Great, thanks, Richard. Just a question from Callum, which has just disappeared. That Richard, you were involved with a clay spreading trial at Badgingarra with West Midland Group. Do you have any idea of the yield increase break even in the lower rainfall zone compared to Esperance?
Thanks for that question, Callum. Yeah, this was a couple of trials that actually Steve Davies originally set up, and we inherited and worked with them for a few years. Look, we didn't do economic analysis on that, so can't actually answer the question. I think Steve Davies would probably have better data on some of the economic analysis because he's done quite a lot of these trials across the wheat belt, including the northern ag zone.
So, and we might also be able to just have a look at the results and put some of your own figures in, Callum, like if you know how much, the clay costs and the spreading, and look at the yield results and do a few rough back of the envelope sort of.
Yeah, I think there was a few conversations had. I remember going to the actual trial sites and essentially it was decided it wasn't worth doing unless the clay was on your property or your neighbour's property. But yeah, maybe I'll have a conversation with Steve then. Thanks for that, Richard.
Yeah, I think the rule of thumb that most people have with clay spreading is don't move it more than 200 metres from the burrow pit if you can avoid it. Certainly not more than half a kilometre, because the fuel costs of moving it around start to blow out and really offset the benefits that you're going to get.
Okay, now one last question from Peter. Peter, would you like to unmute yourself and ask this question, and we'll perhaps just, try and get a quick answer so we can have a good little break before Richard starts.
Yeah, no worries. At the end of the day, it was just a question about how best do we help farmers map their soils, because it is vital, to help them be more strategic, when they've got all these different options, and some options, strategic tillage or claying are going to be better in certain circumstances depending on what their soil is. But so they really need to know their soils, and they do know them, and they probably can map a lot of it out of their head. But, how best do we help that process, I suppose? And it gets back to, is that mapping, and interested in Maria's sort of project to help that process.
I think it's hard because when I was doing stuff with blue gums, that sort of, I think it was a couple of $1,000s a hectare establishment cost. So, it's quite capital intensive. And I tried to get them to do intensive surveys, and it was hard work, and even with sort of quite an expensive crop. So it's an issue, and I think that's where things like radiometrics and the other things hold promise, because they can be applied relatively cheaply, so you can get an idea of that spatial variation. But I've seen a few things where people have got all the digital information, and then they sort of get a wax pencil out and sort of draw lines around it. So I guess in the ideal world, you'd have the digital information, have a good understanding of what it means, and then produce clear maps of management responses. And I guess that's what we're interested exploring with Maria, is for water repellency, and probably apply to wind erosion as well. But having those, having the ability to do the mapping, come up with surface, and then spit out sort of recommendations. So, well, this is where you clay, this is where you do whatever your major areas of interest. But I think it's been pretty haphazard up to now. But
and just one other part of that question was somebody advised me that the thorium layer, I think it's in radiometrics, is quite good for identifying gravel, which can be associated with water repellents. Is that relatively accurate, or is there confidence in that layer?
I think we should come and have a chat to you.
Yeah, okay.
Because we've sort of, Maria's only just been at it for a week. And
Okay. Well, she doesn't know yet.
Yeah. That's next week. You could give you a call next week. Yeah, it might be useful to come have a chat to you because the aim is to make it as useful as possible, and it could well be that people are doing radiometric surveys and already finding these relationships.
Mm.
So it'd be good if we can catch up with you.
No worries.
Sooner rather than later.
Great. Thanks, Richard. Thanks, Peter. Thanks, everybody, for your questions. It was really great to have, that bit of discussion at the end. So I really appreciate it. And thanks, Richard. That was fantastically comprehensive and it's given us a really great idea about, soil formations and the history of soils in WA and what these guys are going to be dealing with. So I really appreciate your time and your input. And we look forward to seeing the soil CRC work that you're working on as well. So.
Thanks. Happy to do it.
Terrific. All right. So we'll take a break.
But Richard did tell me that his kids used to hate going on these long trips with him because he'd always be stopping and digging holes and fossicking around, looking at rocks and so.
Yeah, we had one craft shop, one road cutting.
They'd be loving it. Oh dear, they didn't realise how lucky they were, I'd say, Richard.
No, they sort of sit in the back seat with PlayStations, or not PlayStations, I don't know what they're called now, little games.
Okay, so shall we kick off?
Yes, thanks, Richard. So we'll kick off with Richard Bell from Murdoch Uni, who will take us through some soil organic matter and soil chemistry information.
Okay, so what I'm going to do actually is borrow from the soil quality ebook on soil organic matter. I thought rather than prepare something original, I would just go to that source and go through some material that they've presented. So as you know, there's these are available as ebooks. And another publication which is really good is published by GRDC on managing soil organic matter. And Fran Hoyle is the author of that. DPIRD has a frequently asked questions about soil carbon and soil organic matter on their website that is worth looking at. And of course, there's a whole range of soil textbooks and all of them will have a chapter on organic matter. And so for Western Australians, I think the challenge of soil organic matter is summarised in this quote from the ebook, which says, land clearing for agriculture has led to a loss of soil organic matter over time in many West Australian soils. Continuous cropping and soil disturbance linked to historic farming practices has resulted in significant losses of organic matter associated with faster decomposition and erosion. So what I'm going to do is come back to these slides later on, but what I'd like to do now is focus on this ebook and just go through some of the material that is there. Can you see that?
No, so we can see your PowerPoint's file still.
Right, okay, I'll close that. Yeah, I think I need to stop sharing. And yes, flip over, yeah. You should be able to see it now.
Yes.
Yeah, okay. So we've got Andy talking about compost, and Lynn Abbott's going to talk about soil biology in the afternoon. So I thought this was just a good opportunity to share some key properties, observations, processes around soil organic matter as it relates to both of those topics. So the ebook is one of many that is either published or in production. So they're really a great resource because they're all based on Western Australian examples and research done locally. Dan Murphy and Fran Hoyle are the leaders in this soil organic matter publication, but others have contributed as well. So a couple of key dot points. That soil organic matter is critical for soil ecosystem services and is an important part of the natural capital of a soil material. Soil texture, in particular the clay content of a soil, determines the potential for organic matter to be retained in a soil, but climate, which affects growth and biological productivity, drives the inputs and losses of organic matter in the soil. Across landscapes, you can get big variations in organic matter, both at small scales and large scales. So there's the challenge of sampling. The next dot point is that building organic matter in soils is a slow process. It's an incremental process, but it's worthwhile because we know organic matter provides many biological and chemical fertility benefits for soils. The organic carbon in soils in Southwest Australia has been mapped to some extent. This figure here shows areas where they have reasonably good records of the organic matter level, but you can see that there are large areas where we just don't have enough data to say for sure. But what we can see already is that close to the coast where the rainfall is higher, the stocks of carbon in the soil are higher than as you go inland into the drier areas. And that tells us that the rainfall is really a big driver of what's going to happen here. And from the work that Dan Murphy and his group have done, they've looked at which parts of the state already have close to the potential amount of carbon in the soil based on climate, and which areas seem to have the potential to grow more carbon because of higher rainfall. And you can see that what they're suggesting is that in these drier northern warmer areas of the wheat belt, the potential to build soil carbon is probably somewhat limited compared to the wetter coastal areas and southern zones. So here's a little video.
Over 1,300 soil sites across the southwestern agricultural region of Western Australia were assessed for a range of soil properties and site variables to determine the factors associated with changes in total soil organic carbon to a depth of 30 centimetres. Site variables including soil type, bulk density, clay content, pH, electrical conductivity, water repellence, disease, long-term climate data, and on-farm management information, such as nutrient application rates, stocking history, rotation, and use of amendments were used in a meta-analysis to determine the primary drivers for measured differences in soil organic carbon. Analysis indicates that temperature and rainfall are primary factors influencing the variation in soil organic carbon content for Western Australian farming systems. Data shows higher soil organic carbon stocks are associated with increasing rainfall, a primary driver of plant productivity. In low rainfall environments, the potential to influence soil organic carbon stocks is more constrained when compared to higher rainfall environments, which demonstrate a wide range in soil organic carbon values associated with soil type and management. While unravelling the influence of geographic position from rainfall and temperature is difficult, data suggests environments with an average annual daily temperature of more than 17 degrees Celsius are limited in their capacity to accumulate carbon in soil, showing a narrow range of carbon values. Sites where average daily temperatures are below 17 degrees Celsius show a wide range in soil organic carbon values, which indicates a greater potential for management, soil type, and smaller scale climate variables to influence soil organic carbon. Results from this study suggests the capacity of environments with an average annual rainfall of less than 450 millimetres and an average daily temperature higher than 17 degrees Celsius are limited in their capacity to accumulate carbon in soil. As shown on this map, the highest potential for future carbon storage is associated with loamy soils and higher rainfall environments capable of supporting higher net primary productivity.
Let me just double check that you are able to hear that okay.
I could. It was terrific.
Good. I did check it yesterday with somebody else, but that's good. There's a few more to come. So if we look at soil profile, we find that most of the carbon is in the upper layer, the upper 10 or 15 centimetres. In fact, 60% of the organic matter is probably in that upper 30 centimetres of the soil. Sorry, 60% of the carbon in the upper 30 centimetres is in that 0 to 10 centimetre layer. And of course, it's subject to loss there from erosion and from decomposition. The organic matter in the soil is actually a complex mix of different materials. So it's not a single material. And those different materials have different origins and different composition. So a portion of the organic matter in the soil is what we call dissolved organic carbon. And while it's only a small proportion of the overall soil carbon, it's quite an important pool for biological activity, microbial activity, that this is the carbon that often is driving a lot of the activity of bacteria and fungi in soils. So much so that in some places they measure the dissolved organic carbon level in the soil as an indicator of biological activity. Of course, a large portion of the carbon in the soil, the organic matter, is the humus. But there's also the particulate matter, which is an intermediate form of carbon that's in the process of being broken down into these more resistant and humus fractions. And that brings us to this little animation here, which is about the cycling of soil organic matter. So I'll play that.
Soil organic matter cycles continuously between its living, actively decomposing, and more stable fractions. When plants and animals die, they are decomposed to become part of the soil organic matter. Soil organisms fragment and consume organic residues, gaining energy to grow and reproduce. Fresh residues are broken down into smaller pieces and become part of the particulate organic matter fraction. As the material is further decomposed, a proportion of more biologically stable material enters the humus pool. Nutrients and other compounds not required by microorganisms are released as a result of this transformation and can then be used by plants. As the organic residues continue to decompose, a very small proportion becomes chemically stabilized, enabling it to resist further change. Again, nutrients superfluous to microbial requirements are released and are made available to plants. Nutrients resulting from organic matter transformations can supply up to 80% of the plant's requirements. Carbon dioxide emissions result from these biological transformations.
I should stress here that what we're talking about here is organic matter cycling in a soil as part of the natural ecosystem processes of soils. And of course, what Andy's going to talk about in the next presentation is about adding additional carbon in the form of compost, which is able to generate new processes that perhaps don't occur in the natural soil. It's also worth mentioning that something like 2 to 4% of this organic carbon in the soil turns over or breaks down each year. So if you don't continually add carbon into a soil, the level is going to gradually decline because of this natural decomposition process. So even to maintain organic matter levels in soils, we've got to be adding as much as is decomposing just to retain the steady state of the current situation. Why are we interested in organic matter in the soil? Well, it's because it's involved in various biological functions, chemical functions, and physical functions, all of which go towards a healthy soil. Fundamentally, organic matter is an energy source for biological processes. So bacteria and fungi, even the fauna in the soil, are consuming this material as their energy source in order to live and to carry out their other functions. The organic matter in the soil is a store of nutrients, particularly nitrogen. Almost all of the nitrogen is stored in organic matter. Much of the sulfur is stored in organic matter. And what's commonly not understood is that quite a lot of the phosphorus in the soil is also stored in organic matter. And this organic matter contributes greatly to soil resilience, the ability of the soil to cope with stresses, droughts, and other disturbances and retain its function. Chemically, the surface area of organic matter helps with the retention of nutrients. Per unit weight of organic matter, it has a very high surface area, and that allows it to interact with nutrients and hold on to nutrients, particularly cations. The organic matter helps with the buffering, pH buffering of a soil. Where there are heavy metal or pesticide contaminants, it can help with immobilization. In the case of herbicides, for example, the breakdown of many herbicides by microorganisms in the soil is achieved because the microorganisms simply use those compounds as energy like any other carbon compound in the soil. And then the physical functions of soils, its formation and stability of structure depends on organic matter, and of course the water retention of the soil. So all of those. One of the key properties of organic matter, particularly organic matter that's being added into the soil, is its carbon to nitrogen ratio. In soils, the carbon to nitrogen ratio is generally in the order of about 10 to 12. So if you do a soil test and you compare the carbon and the nitrogen levels, you'll find the ratio comes out at about 10 to 12. But when we add material to the soil, it may have vastly different C to N ratios. Legume, stubble or residues have relatively low carbon to nitrogen ratios. Grass legume pastures, somewhat intermediate, whereas cereal residues, oats and wheat, have quite high carbon to nitrogen ratios. And that can result in immobilization of nitrogen in the soil, because as those high C to N ratio materials are decomposed, the microorganisms actually consume available nitrogen from the soil temporarily. And the photograph here shows these strips of yellow coinciding where the crop residue from the harvester was dropped in the previous year, producing a high load of high C to N ratio material that is temporarily immobilizing that nitrogen. Of course, that nitrogen will eventually come back into the soil mineral pool as the microorganisms decompose. I mentioned cation exchange capacity. Soils may only contain 1, 2, 3% organic matter, and yet that tiny amount of organic matter can have a very major influence on the overall cation exchange capacity of the soil, as shown in this table here, which is cation exchange in units of charge per 100 grams of soil. So you can see sands and sandy loam textures, they have quite low cation exchange capacities compared to clay soils. But per unit weight, organic matter and humified organic matter have extremely high cation exchange. And that's related to their surface area and also the chemical compounds or molecules that are present on the surface of the organic matter that help it to hold on to cations. So there's quite a lot of material in this ebook, and I'm just picking out a few highlights here because we don't have time to go through it all, but I would encourage you to read it yourself from cover to cover. Storage of water in the soil is one of the functions of organic matter, because organic matter can hold several times its own weight in water. So if we were able to increase the organic matter of content of a soil from 1% to 2%, we would hold an extra 2 to 5 millimeters of water in the soil. So when we think about 5 millimeters of water, that's has the potential to produce an extra 100 kilograms of grain using 20 kilograms of grain per hectare per millimeter of water, which is the standard figure that we use in the French-Schultz equation. So that looks quite promising, but in order to increase the organic matter content of a soil from 1 to 2%, we would need to add something like 100 tons per hectare of organic matter, because most of that is going to decompose and leave only a fraction of that 100 tons in the soil to provide that function. So whilst we do know organic matter is important for holding water in soils, we shouldn't overestimate the potential for increasing water content by small increases in organic matter content of the soil. I'm going to skip over a few of those pages. Another of the important concepts, I think, in this book is about what we call attainable organic matter content and potential organic matter content. as opposed to the actual organic matter content. So the actual organic matter content is what's in the soil today under the current management. The attainable organic matter content is based on the climate in which that particular site or soil actually exists. So it's about the radiation, the temperature, the rainfall. And then the potential organic matter content is what you could hold in that soil based on its clay content, its bulk density, its mineralogy, and its depth. So in most cases, what we're looking at is changing management to increase from actual to attainable soil organic matter content. We probably can't go to the potential organic matter content unless we're in a system that's applying a lot of organic inputs such as compost, or we're changing the effective climate through irrigation. The next important concept I'd like to stress to you is this concept of soil organic matter balance. It's about outputs and inputs, and I'd just like to show you this little video.
I'm often asked why soil organic matter levels are different in different soils. We think about a soil, the pieces of plant material that drop on the soil start to get broken down by microbes. The amount of organic matter that enters the soil is very dependent on plant productivity. And if we think about this as a tipping scale, on this side we have the amount of plant production, and that's very much related to the type of crop we're growing, so the amount of biomass that it produces, the climate, so how much net primary productivity can be grown, and of course how much we offtake in terms of a product from an agricultural aspect. On the other side of the tipping scales, we have the microbes, and they're using that organic matter as a food source. So they're breaking down plant residues as they enter the soil. The other loss mechanism is erosion, whether that be by wind or water. So at any given point in the field, the organic matter levels can vary through seasons and through years, depending on the inputs and the outputs. The other thing we need to think about is soil type. Not all soils are the same. Some soils have more clay, and the important aspect of clay is that the clay physically protects the organic matter from breakdown. Microbes cannot eat through the clay platelets to get to that organic matter. So soil type is certainly an important aspect, as well as the inputs of plant material and the rates of microbial breakdown.
The management factors that influence soil organic matter, Dan already mentioned the net primary productivity. This is very much around climate and other aspects of soil management, whether we're dealing with crops or pastures, whether we're adding green manures or cover crops into the farming system, what the strategy is for stubble retention, whether we're controlling erosion, and what other soil disturbance events are occurring in that farming system. And finally, whether in the farming system there are organic amendments or inputs in the form of compost. The final thing I'd like to leave you with is carbon stocks can take a long time to build up. And this is an example here from a case study on the Esperance Sand Plain. And it was a study done by UWA comparing annual pastures with perennial pastures in a reasonably high rainfall zone. And so the hypothesis was that the perennials, because you've got deep-rooted plants that are there all year round, would, over a number of years, build up the soil organic stock to a greater level than in the annual pasture. What they found was that even sites that were up to 34 years in perennial pastures, there was often very little difference in the organic matter content of those different soils. They also did some modelling, organic matter modelling here, and found that actually under the perennial pasture, if you keep it going long enough, 40, 50 years, you will be able to measure some increase in soil organic matter content, but still not a large amount. And I think that's an important reality check when we're talking about soil organic matter and what's possible and what's not possible. So I'm going to wrap up there because my half hour is up. We could take a bit of time answering some questions, and then I think we'll all be ready for Andy's presentation.
Thanks, Richard. That was really great, and a fantastic example to use that book, because yeah, I have to say I've downloaded it, but I haven't really got into it. But being taken through it like that is fantastic. Peter had a question about how to monitor change in soil organic carbon and the best method and carbon test.
Yeah, look, this is, I guess there's two aspects of this. One is if you're just in a production system and you want to know what's happening over time. And then the other aspect is if you're in a carbon offset or carbon sequestration program where you need to be able to measure and validate. So if we're talking about the latter, as carbon sequestration or carbon offset system, there are prescribed guidelines and rules on how you have to sample and what the methodology you should use for the analysis of carbon in the soil. But if you're just in a farming system and you're interested in productivity of the land and what the trends are over time, there are some guidelines there about how many cores you need to take and the uniformity of the area that you need to sample from, and of course sending the and standardizing the depth. We know that organic matter is quite stratified, so the concentration drops quite sharply with depth. So small variations in the depth of sampling that might not seem significant, you only push the pogo stick in to 8 centimetres rather than 10, could end up biasing the organic matter level that you've measured quite significantly. But I think most of the sampling programs for fertility management of soils suggest you need to find a uniform area, and you need to take something like 25 to 30 0 to 10 centimetre samples from that area in order to make sure you've got a pretty representative sample. And then of course you have to make sure the sample either gets to the lab quickly if it's moist, or dry it, sun dry it, air dry it quickly so that there's no further change or breakdown of the sample, and then get it to a lab that is certified and can demonstrate that they're able to produce reliable results. And in terms of the time frame for organic matter, probably 3 to 5 years sampling frequency. I don't think it'd be realistic to expect to measure big changes within 1 or 2 years.
Thanks, Richard. I actually had another question, Felicity, if I can butt in quickly. Yeah, just regarding that last point about the perennials and the annuals. I've often thought, and even we had a Graham Sterling, who you may know more in the veggie area. You know, he was over here and talking about, you know, the effect if you get rainfall in summer, you know, and the devastating effect that can have on carbon loads. But he sort of said, oh, but over here you probably don't have that much, you know, where you have a dry summer, then it's just sitting there, not really doing anything. So I often think, you know, when they talk about, you know, that perennial or that system of green, you know, year-round green pasture, how much does that you know, to build carbon, how much does that actually apply to Western Australia when we have such a dry summer? You know, can we sort of maybe adapt that system a little bit and say, you know, when it's dry, don't worry too much about, you know, trying to grow summer crops and seeing a lot of it not actually be successful in our climate?
Well, a couple of things there is, it depends where you are. Of course, close to the coast and particularly along the south coast, summer rainfall is fairly frequent. Most years you would get a significant amount of rainfall, and so that under the warm conditions, it does activate soil biology very quickly. And so that can be a net loss of carbon. Whereas at least if you've got plants growing there, they're offsetting that loss by producing more carbon. And the climate change scenarios suggest that we're going to get more summer rainfall rather than less. But I guess in many places, growing summer crops is still very much an opportunistic exercise, that you just look at what's happened in the late spring, and you might look at some of the longer range weather forecasts, and if you've got moisture and likelihood of further rainfall during the season, then you might go for it. When I saw a farmer down at Esperance who put in a sorghum crop and grew 6 tons of sorghum grain. It was an amazing crop. The farmers on the Darling Downs would have been very proud and pleased to have grown a sorghum crop as well as that over the summer, but it might be a 1 year in 10 proposition.
Thanks,
And of course, with perennial pastures, I mean, they're there and they will respond to that rainfall and maintain that biological activity.
Belinda's asked a couple of questions around optimum organic carbon levels in the soil.
Yeah, look, I guess it's a question of you'll take what you get. And as the presentation suggested, climate is going to be, and clay content of the soil is going to be a major driver of what's actually possible. And the only way that you're going to drive carbon levels higher is if you spend a lot of money with Andy and put a lot of compost in. And so if you're doing that continuously, you can build up levels further. But if you're relying on natural rainfall and the growth of annual crops, then it's going to be very much determined by how much you can grow, the rainfall and the temperature, and how much clay is in the soil to bind and hold on to that carbon. Yeah. And I recently saw a paper, it wasn't from Australia, it was from an international study, which asked the question, you know, what is the optimum level of organic carbon? And is there evidence that that level is related to yield? And actually the conclusions were pretty weak of being able to say you must have this level of organic carbon in order to have a functioning soil.
Yeah, I wonder if it's also about the benefits of a certain amount of organic matter or organic carbon. You know, the equations of a ton of organic carbon will hold X amount of water in the soil, and if a ton of carbon is broken down in the soil, then it will release however many kilos of nitrogen and phosphorus and sulfur. Is that, I mean, that's sort of a way of quantifying it, or yeah.
Yeah, look, you've hit on a good point, I think, and that is that, you know, organic matter is not a single compound. It's a mix of compounds, and for biological activity, it's the compounds that turn over more actively and rapidly. That's why the soluble organic carbon is important. But Dan Murphy and his group have looked at organic carbon across the southwest of Western Australia, and what they found was that organic carbon levels actually increase in acid soils. And their explanation is that because the biological activity is suppressed in the acid soils, it's just not turning over and breaking down. So yes, there's more, but actually, is that what you want, or do you want carbon that's turning over and active?
Yeah. So I think this leads into your second question, Belinda, around soluble nitrogen fertilizer removing soil carbon. And I wonder, Richard, if it's about that soluble nitrogen fertilizer actually feeding the biological activity, and then it's the biological activity which is actually breaking down the soil carbon and in effect removing the soil carbon from the system. That's just a hypothesis.
Yeah, look, I think that is probably correct. If the input of carbon is not sufficient to offset the rate of decay. And so if you're adding more nitrogen to speed up the rate of decomposition, then to maintain the carbon levels in the soil, you need to be increasing the inputs. And I don't know if it's so clear in Western Australia, but certainly in Eastern Australia, they are seeing in their long-term cropping soils declines in soil organic matter. And I think it just goes back to this question of inputs and outputs. So if you speed up the output by more active biological activity with the nitrogen in the system, then in order to maintain organic matter level in the soil, you've got to boost the inputs as well. And there's various ways to do that. And one of them is getting back to rotations with pastures. So you've got periods where you're actually actively building carbon. And maybe the continuous cropping system is at risk of those long-term erosions of soil organic matter.
Yeah, see, my understanding of it was that it's the relationship of the microbes with the plants that sequester the stable soil carbon. And if you're adding nutrients and inputs into the system, that means the plant doesn't have to set up that relationship with the microbes and put out carbohydrates through the root system, then you're not going to get that sequestering of carbon and the build of organic matter. And hence why adding soluble nitrogen kind of breaks down the cycle, because the plant's then not adding it in.
Yeah, look, I still think it will come back to inputs and outputs, that if you're decomposing carbon faster than you're putting it in, then there'll be a long-term decay in soil organic matter levels.
And I think with nitrogen fixing bacteria, it's certainly important to make sure that you've got a good population of nitrogen fixing bacteria, so that you are providing an environment for plants to be able to fix their own nitrogen in that respect. So that would certainly be helping towards building soil carbon without having to add nitrogen.
Yeah.
Great, thanks, Richard. We might keep moving on, but if anyone's got any other questions, please pop it in the chat box. Yeah, Freya's just having, maybe Richard, you could provide some advice for Freya about downloading the Apple books. I'm not sure if you need to be on an Apple, Apple device to be able to download it. You might not be able to download it onto the computer.
Yeah, it's only for an Apple device.
Yeah. So if you've got an iPhone or iPad. Thanks, Richard. That's a fantastic introduction for Andy. So I appreciate that, and I encourage everyone's got the link to be able to download those books and have another look at them in your own time. But thanks very much, Andy, for joining, and Chris as well. So Andy's joining us from CWise. Some of you may know a bit about CWise, but they're a composting company, as far as I know. But Andy, feel free to introduce yourself and explain a bit more about what you do and your experiences, and I'll leave it up to you. Thanks, Andy.
Okay, I'm just starting to share my screen, and here we go. Fascinating discussion so far. What I've just done is, listening to Richard and the questions, I've thrown an extra couple of slides in, which may address some of the questions. I hope that doesn't disrupt my presentation, but if I forget, when I talk about cauliflowers later, I've got some examples about soil carbon levels and how they were built up and what the effect of that build-up was, and I've got some percentages there. I've also got some examples of some silage and hay crops that have been grown with 0 inorganic fertilizer, and it's at relatively low amounts of compost. Because one comment Richard made was, send Andy Gulliver lots of money and you'll solve your problems. Of course, we'd go broke if that was true. The solutions that we provide have to be cost effective for the farmer. So we're driven by the economics of farming. The other thing, just listening to the question about the Nicole Masters question about nitrogen driving down soil carbon, I think the conventional wisdom says the use of lots of urea is driving down soil organic matter levels. We've been playing around with liquid compost extracts more recently, where we're combining that nitrogen with the highly soluble, highly humified components of the compost. And there's a synergy there, it would seem, the same as there's a synergy between compost and clay. So there's some exciting things. If I forget to mention them along the way, someone can pick me up on it later. So what I would like to do is I'll just play around with the screen here. Right, there we go. Now, what I've done is I've stolen a presentation from a 6-part series that ourselves and one of our ex-employees put together for a national soil program. And I've skipped the parts about the physics and the chemistry of the soil and the physics and the chemistry of compost, because obviously that's been dealt with elsewhere. And I'd just like to acknowledge that John Barton was one of our ex-employees and started a business on the East Coast called Charlton and Bang. I just want to acknowledge that some of this is his work as well. So what we'll cover today is ecosystems thinking, the idea of balance, a little bit about policy or history, and of course, most of the people on this webinar receive their money through federal government funding. So I can say things about federal government policy that maybe you can't. So just indulge me on that. A few principles about biology. We've covered some of them already, but I'll try and put them into context from a soil management point of view and from a composter's point of view. Some practical stuff, and then hopefully at the end of that, there'll be a reason why that managing soil organic matter is really important. Now, I'd just like to do a check. Is my audio coming through okay, and are the slides working?
Yes, it's all good, Andy.
Okay, I'll carry on then. And a few apologies I'll make. Some of these ideas may be challenging and a stretch for the imagination, challenge conventional wisdom. I might have a slightly twisted view on soil carbon. I may be politically incorrect, and some of the analogies are a bit gruesome, so just be aware. And I'd also like to acknowledge, I won't acknowledge people's work as I go through, but I do acknowledge that I've really combined ideas from a whole heap of people. All these names would be familiar to you, I'm sure. What I've done is I've tried to effectively synthesize those ideas into some sort of coherent narrative around soil. And it really boils down to this one thing. And I do hope Lynette Abbot, she may not be online yet, but this is the sort of stuff that Lynette Abbot's been talking about for 20, 30 years, and now her day has come, I think. And the basic idea or the proposition is that there's a huge genetic diversity in the soil that drives healthy ecosystems and healthy crops. And if you like, the age of biology has come at last. A lot of our soil management theory has been driven by physics and chemistry, and because we didn't know much about the biology, because it was difficult to measure. That's all changed in the last 5 or 10 years, and it's quite exciting. The next proposition is that building biodiversity and increasing biological function is critical for success in soil, and that this is not a well understood concept. It's really difficult to sell. Biology, the farmers don't really understand the concept, and why would they? Because that's not been their training. And the conventional agronomists don't, because it's not their training, and certainly selling it to politicians who make policy is difficult as well. But biology and microbiology is the driving force for organizing and controlling soil functions. Now, that's not to say that chemistry and physics of soil is not important. It's just that we've got to get everything in balance. So thinking a bit about balance, everything will always be in balance. Society, nature, and economy. We're driven by economic rationalists that say we have to have jobs and growth, and if you're not thinking about jobs and growth, then you have to talk about jobs and growth, and so on and so on. And we forget about building social capital as a community, although we're seeing some of that with the COVID experience of the last year. We've started to realize how important community and society are. And of course, we don't as a community value natural capital, which arguably is the driver of our economies and our societies. But that's a philosophical question that I won't get into today. Another concept idea is this idea that we're living in the Anthropocene period, the period in which human activity has been the dominant influence on climate and the environment. We're the first species in history that can actually change the functioning of the planet. That's an astounding achievement. And what have we done with that? Well, we think about it. Conventional wisdom says we're consuming the Earth's resources at about the rate of 4 planets. So without a planet B, C, and D, we actually do have to change the way we do things. At the same time, you have to ask yourself, well, what have we done to ourselves? We've changed, not only have we changed our management of soil, our production of food, but we've actually changed not just the health of the soil, but arguably the health of the humans as a species, or certainly in Western civilizations. So what are we going to do about that? We're going to perk up and take action, and like the ostrich, run. I'm not sure where we're running to or from, or we're going to take the traditional policy response in Western culture, which is basically ignore it. And if we ignore it, maybe it will go away. Well, I think you're seeing in the media today that carbon is not going away. Something else has changed though, big data. And this has changed the depth of our knowledge about the functioning of ecosystems. I'll come back to that, but it's really quite an exciting area. I would argue that we cannot imagine in 2021 where we will be in 2025 because of the new knowledge that big data is providing, even in soil science. But you go back to classic soil science, and this is, a slide you might have had in high school science lessons in the 1970s, where soils generally are a balance of chemistry, physics, and biology. And I won't go into the detail of that. It's something that I'm sure we're all familiar with. And our farming systems, for better or worse, and it's not a value judgment, our farming systems have tended to dominate in chemistry, because if we added chemistry, it worked. And if you look at the history of the chemistry, right back to the discovery of Haber-Bosch in the early 20th century, and how that made fertilizers more freely available. You look at the Green Revolution, you go back and read Norman Borlaug's papers. The Green Revolution wasn't actually about the availability of chemicals from the industrial war machine, which is once again a conventional narrative. But Norman Borlaug's achievements, and he got a Nobel Prize, was for plant breeding, to breed varieties of cereals and rice that would address the impending famines in South America and Southeast Asia. And those of us who were around in the 60s and 70s will remember the terrible famines of the 60s and 70s, particularly the Biafran type famines in Africa. So Norman Borlaug's work led to varieties which fantastically increase yields. But to optimize those increased yields, we needed growing systems, and that's where using inorganic fertilizers and the new breed of plants had a fantastic results. And a curious thing, the question about nitrogen was curious, because I believe I got my facts right here, that our increase in cereal and rice production per head of population has trebled since the 1970s. That's a tremendous achievement. But our increase in nitrogen consumption has gone up 9-fold. So the increase of food has come at the use of nitrogen, and arguably and then the decline of soil organic matter, because the use of nitrogen, you effectively mine the soil organic matter in the soil. The one thing I would check in that is that the 9-fold increase in nitrogen, I'm not sure if that's per head of population. So just a word of warning there. So we think, I'm sure everyone's seen this slide before. What did Roosevelt say? The nation that destroys its soils destroys itself. But he was talking in the context of the 1930s and the Okies in Oklahoma walking off their land because of the Dust Bowl. And then you argue, but that was the 1930s, nearly 80, 100 years ago. Surely we know better than that. And yet Sydney over a decade ago was covered in a blanket of dust. And one of our largest exports that year arguably was the topsoil that we sent to New Zealand, for which they were very grateful. But then you say, but surely we've learned. But no, 2 years ago, in Hay in New South Wales, that's a dust storm encroaching on the town. So it's still an issue. And the issue can be dealt with to some extent by how we manage soil carbon, soil organic matter. And if I'm talking to a more general audience who think that carbon is possibly a pollutant because of the carbon dioxide, well, actually, no, carbon is a driver of life on Earth. All life on Earth is carbon-based, and we should be proud of that fact. And we are here because of solar radiation being captured by plants which grow on that thin layer of topsoil. So there we are, we're capturing energy from the sun, energy stored in the carbon in the plants that drives nearly all living processes on Earth, and that thin layer of topsoil supports all life on Earth. An astounding story when you think about it. And quotes from the past again, 1908, Cutler and his associates said the depletion of soil humus supply is apt to be a fundamental cause of lowered crop yields. Gosh, we knew that in 1908. Why are we even having this conversation in 2021? We are having it because we need to understand history and how we led ourselves to this point. And we should not blame the farmers for their use of fertilizers, because they were using best practice as we knew it at the time. The thing about time is we actually have to learn to adapt, and times are changing. Going back to photosynthesis and that carbon pump, green plants are effectively the carbon accumulators for that thin layer of topsoil on the Earth. So we know that building soil carbon requires plants and the power of photosynthesis, or the carbon pump. That converts solar energy into carbohydrates. That uses CO2 and water. And the limiting factor is water. And interesting, the comments about climate and water earlier were limited to the limitations on building soil organic matter. And then with that process converts carbohydrates into complex molecules, and then that provides the fuel that drives living processes, provides food and fiber in crops, and the plants capture and share the carbon in the soil. The roots go into the soil, and there are exudates that go into the soil. So 30 to 40% of captured carbon is exuded by the roots. But you say, well, wait a minute. Nothing in nature does anything for nothing. So why would a plant, having gone to all that trouble to evolve a process to use the energy of the sun and take CO2 and water and turn it into this fantastic energy source, why would it give it away? Well, you think about it, a plant root can only occupy a certain volume of soil. And that volume of soil also has to supply all the mineral elements that the carbohydrates combine with to form living organisms. Once that soil is mined, the plant effectively will run out of supply. By supplying a carbon source to the microbes in the soil, those microbes in the soil can occupy a much, much larger volume of soil. So that's particularly the bacteria and the fungi can occupy a huge volume and can actually then bring those nutrients to the plant and trade them for the carbon products, because the bugs can't produce their own carbon products. So that's a fair trade. And that's the sort of system we're now understanding, but we're also understanding we have to curate that microbiological or biological process in the soil to optimize the production of our crop plant. The other thing about biodiversity, and the slide indicates there that different plants have different above ground biomass, but vastly different below ground biomass, and there are interactions between the different plants which actually causes more synergy. And if you want to look up the Jenner biodiversity experiment in Europe, you'll see that the number of species is directly related to the plant biomass. More species, more biomass. So what did Garneau say? He said, well, the most significant opportunities may be in the area of soil carbon sequestration. Now, I'm misquoting him about a bit, because he was talking about climate change. However, if we knew that in 2008, why are we still talking about this in 2021? Time for a break. If there are any, now I can't see the questions on my screen, so I'm not sure if there. I'll just ask if Felicity, are there any burning questions at the moment, or do I carry on?
No, I don't have any burning questions at the moment. But if anyone,
okay, I'll keep racing along. Felicity, if something pops up, feel free to break in.
Sure.
So then, and this is one of the slides I slipped in because I suppose people, Richard said I was going to talk about compost. I actually wasn't going to talk about compost because that would sound like shameless self-promotion. But what I would promote is there is a whole compost industry, and farmers, certainly we've helped farmers make their own compost from their own wastes. So there's a whole compost industry that's out there that the farming industry can tap into. And of course, but then tap into what is a compost? And I like the analogy from the Soil Health Guide that effectively said that, and just checking my numbers, that I think it was Richard said, you'd need 100 tons of organic matter a hectare to increase the organic matter by 1% after you've allowed for the decomposition of the labile carbon. The thing about composting is effectively we're doing what nature does over maybe decades, we're doing in weeks by actually concentrating that carbon. We're actually burning off that labile carbon as an energy source for our bugs. And then the bugs are transforming the remaining carbon into humified products. And it's those humified products that are the powerhouse of the soil. And so if you like, composting is a carbon concentrate, but it has to be the right type of carbon. And unfortunately, there are a lot of products called compost that are not really compost. They're really just labile organic matter that's been thrown around in a pile for a while, and people call it compost. And the poor old farmer would never know the difference. And the other thing about compost, of course, is how do we know that they've been managed properly, the process has been managed properly, and that we're not actually spreading things like Phytophthora and Pythium and so on through plant material that's not been properly processed. And if you're looking for composting organizations, I'd highly recommend you go to one that's got a third-party, independently audited quality assurance system in place. That's my comment on the compost industry. Then on the compost process, I'll just throw one slide. I did throw one slide in there, but unfortunately it's still on hidden slide. So I'll just say that there are a couple of things that really matter with composting. One is to get the right blend of ingredients, and the critical thing there is carbon to nitrogen ratio. It's been mentioned before, and you've got to get it right at the start of the process to end up at the right endpoint. The next thing is water. Water is the on-off switch for living processes, and composting is a living process. It needs three things: food, air, and water. The food we get by the blend of ingredients. The water I talked about. The air, the photo you see there is of a compost turner. And you can see the steam coming out the back of it. That just tells you how much heat is being produced. And that, by the way, that is steam and not smoke. And you put your hand inside those piles, it could be 70 or 80 degrees Celsius, enough to pasteurize the material, which is a critical process control feature to make sure that the product has been pasteurized for any potential pests or pathogens. And composting is not necessarily as simple as it looks. It's both a science and an art, and has to be done properly to get the highly humified products at the end that it's worth paying for in farming. That's enough on composting. I've thrown a couple of slides in about, because then I think Richard also hinted that, well, maybe we'll talk about how compost is used. And my background, which I didn't say before, was mushroom growing, probably starting about 40 years ago. And for that, you have to make a very selective growing medium through a composting process. And because you're growing a fabulous fussy fungus, you have to get it right. What we've done the last 20 years is take that skill and experience and apply it to composted products for other forms of farming. So I like to say to people that I've been making a batch of compost from which I had to make money and employ people for the last 40 years. And I'm really looking forward to getting it right one day. And there's an art, a science, and a skill. Now, where did we start? Excuse me. When we moved to other sorts of crops, this is a macadamia crop with a small amount of mulch around each tree. In the early days, we used the Armstrong method, which was a pitchfork and sheer muscle. We then got smarter and developed machinery, so we could mechanize how we could make it practical to apply compost in farming systems. So in this case, we mechanized for vines. But in the top right-hand corner there, you'll see that there's an area that seems to be missed. In this instance, the grower, now this is in the days before satellite imagery, the grower knew where the poor performing parts of the vineyard were. And so he tagged the different parts of the vineyard, because from the top of the hill next door, he could see the poor performing parts. by putting just this layer of mulch across that vineyard, next year he could not tell the difference across the whole vineyard. And that's the power of switching the biology on and making soil functions work. And of course, then all sorts of other machines and methods got used. I should have warned you to cover your ears on that one. And moving on from there, and of course, if you're working with farmers, there's always someone wants to do it different. So we worked out subsurface applications. This was under drip irrigation, where we would insert a layer of compost, and then when the drip irrigation was moved further out as the tree grows, the dripper would be put above that sausage of material. Now, that was an early prototype, and of course people have developed all sorts of machines since then, but the consequence was, as you can see on the right, there is a sausage of compost under the drip line. Now I'm not 100% sure it's necessary to do that, but it was certainly something that the grower was very keen for us to do. We did something else, well, I'm just going to skip those two slides for a moment. I've just realized I have got a couple of slides I've inserted and then I turn them off. If you excuse me, I'm just going to turn them back on. These are the ones I was talking about earlier, and I said I threw them in and hoped it wouldn't disrupt my presentation, but there you go, I've just disrupted my presentation. So here we go. We'll start again from that current slide. There we go. And that didn't seem to work, did it? I beg your pardon. So let's go back to that. Vegetables and carrots and so on. We've developed a whole range of techniques for how to use compost economically in different crops. So on the left, when potatoes are hilled up, we can put the compost along the planting line, and then in the normal cultivations of hilling up the soil, the compost gets included, but included above the potato tuber. And in that case, this was a winter-grown potato crop, and we were concerned that if we increased water holding capacity too much around the tuber, it may get waterlogged and possibly rot. On the right-hand side is a carrot crop where a different technique, we're just putting a fine tickle of compost across the top surface. And you see that then has just worked into the top 50 mils. That was enough to stabilize the soil, and actually in this case, stop the wind blowing. So one of the problems with crops like carrots in a sandy soil is the wind starts to damage the emerging seedlings because they get sandblasted. By using a little bit of organic matter in the surface, you can effectively stabilize the soil and prevent that erosion. It also then means, the idea was that instead of planting a shelter crop, which might be a wheat or grass of some sort, which you would then have to go and spray a herbicide on later, you could actually avoid the use of the herbicide and avoid the need to sow that crop. The Next crop is cauliflowers, and this was quite extraordinary. This is when people think about the compost, they think, oh, you've got to put it on 10 or 50 mils thick to have it to make a difference. We use compost at 20 cubic meters a hectare. That's the equivalent of a layer 2 millimeters thick, and it made a difference. So that photo on the left shows a uniformity of cropping. So not only did we increase the gross margin by something like $3,000 per hectare, but we cut the number of harvests from 8 down to 3. So when you've got a team of 12 pickers going through harvesting, the difference between going around the paddock 12 times and 3 times is really quite surprising. The other thing, by working with the farmers, because the farmer would say, well, wait a minute, I don't want to put all the compost across my whole land because 30% of my land is the wheel ruts. I want to concentrate it. And so we developed a machine to put, excuse me, put compost along the row where the transplants were placed. So effectively, we concentrated the compost around the roots. So we had a fortified soil around the roots of the transplant. And that actually gave that transplant a flying start. And I actually don't think this is rocket science. I just think you give the plant the optimum conditions you can, and then nature has a fantastic way of looking after itself. Now that then led to another development. We had a broadacre farmer who then said, well, I want to pelletize compost and put it down the tube of an air seeder. And we said, oh, that might compromise the biology in the compost, and we weren't sure about doing it because the heat of the pelletizing process might kill the microbiology. And he said, you're not listening. I want to pelletize it and put it down the tube. And I said, well, we're not sure. He said, I'm the customer. You have to listen. So he actually forced us to do it, and this was his results. But here's the thing: in a wheat crop, you can't afford to put 20 cubic meters a hectare of compost. You know, that might have cost back in those days was costing $1,000 a hectare. But what we did by putting down the tube of an air seeder was we precision placed that high performance carbon right next to the seed. The other thing we found is we found we could reduce the fertilizer, and we ended up with trials showing that not that we could reduce fertilizer 50%, but we should reduce fertilizer 50% because there was no benefit from the added fertilizer. And I think that shows the power of soil organic matter in leading to nutrient use efficiency. And that's, if you like, the holy grail that we're all looking for. So then those trials were, that was 10 years ago. Now we stopped for a whole range of reasons. We stopped that process. And then in the last year or two, we've been asked to do the same again. And now I have, sorry, I've just got to, you can see the screen's gone a bit blank there. Right, there we go. We'll start again from current slide. There we go. So I think this is from last year. Once again, these were trials done independently of us. So we're getting similar results to the same ones we got 9 or 10 years ago. Another slide I slipped in is this was a farm that we grew without the use of inorganic fertilizer. We've used 3 cubic meters a hectare and 5 cubic meters a hectare. But once again, we have to get the economics right. I think the fertilizer budget was $180 a hectare for hay and silage, and we managed to grow a commercial crop in a very dry year. And the farmer's observation was that his neighbor's paddocks all dried off, but where he got the organic matter in, they held on greener for longer, so he got a better finish. And once he had harvested and then had rain, the crops went greener quicker than non-treated crops. So once again, this is work that's going on, and it's not just us doing it. There's lots of people doing this stuff. back to big data, and now I'm going to slip over that because I'm realizing that it's 12:18 and I've got probably about 10 minutes to go.
Andy, I might actually
Stop it there.
Stop you there for a minute. Because we have only got 10 minutes to go, I might actually just open the floor up for questions.
Yep, that's good.
Questions now, if you don't mind. Not that I can see many in the chat, but I just thought we might actually just open it up for a bit of discussion. If people would like. I was interested, I just wanted to go back to a comment you made about one of the landholders wanting to pelletize the product, and your concern about upsetting the biology in the pelletized product. But before that, you talked about the process of pasteurizing the compost, which would also kill, you know, the bad bacteria or, you know, issues with the product, but it would also, I imagine, kill any sort of good bacteria. So I'm just trying to get a handle on what is the biological composition of compost, and I imagine it varies, but yeah, I'm just...
Yeah, and that's been quite a discussion over the last 10 years about what are good bugs, what are bad bugs. Where I've landed on that is the pasteurization up front is really important. To kill those pathogens. The pathogens tend to be anything above 55, and the pathogens get affected more than the composting microorganisms. So effectively, you're compromising all the microbes, but you're damaging the pathogens more than the good bugs, the beneficials. And once you bring your composting temperatures back down again, the beneficials get busy and convert that that carbon to humus. The other question about where we were concerned that maybe there were microbes in our compost that were important, and that's a bit of conventional mythology, if you like, that somehow compost is full of these beneficial bugs. I actually think that it's the humified compost is an on switch in the soil, and it turns on the native microflora. And all that microflora is there. We've just got to help nature by creating the right conditions. So we've tried all sorts of additional microbes to see if we could get a synergy, but we've tended to find, for example, in those original wheat crops, we had an increase in mycorrhizal fungi, even though we did not add mycorrhizal fungi. So effectively, we were switching on native mycorrhizal fungi. So therefore, my concern about killing the bugs in the compost when we pelletized it, we put it under high pressure to pelletize it, was unfounded.
Okay, there you go. And I guess you can take soil, you know, people take soil and get it tested for biological activity. Have you done that with your compost, or can it be done with for compost?
Sorry, I might just stop sharing the screen if that's okay.
Yeah, sure.
Then I can see you. Okay, say that again, please.
I was just wondering if you've, because you can soil test for biological activity in soils, and I was just wondering if you do the same with compost, or if you can, or if it's
yes, there are a couple of labs around Australia who are trying to. They're doing a lot of work on trying to with the new DNA type techniques. There's a lot of work going on that you can identify species and genera, but it's created so much data. We don't really know what it means yet. So we're still finding out. And my practical view is it probably doesn't matter. It's the biodiversity that matters. If we get lots and lots of different types of bugs, is what we want, not a particular one or two, because they're the one or two we happen to be able to measure. Yes,
it's interesting. When I've investigated more of this sort of biological activity, you do need to find out what the lab is actually reporting. So often it'll just report a total microbiome, if you like a total number of bacteria or fungi, but not necessarily say what's active and what isn't. because they will be active at different times of the year under different temperatures and moisture and food availability and all those sort of things. So,
and that's a really good point, because so long as you've got a wide range of biodiversity, then if you've got a dry period or wet period, you'll have the right bugs. If you've got a hot period or a cool period, you'll have the right bugs. So different bugs will dominate, because that's how ecosystems work.
yeah.
And I think it's this man-made thing where we think we have to control everything, but actually all we've got to do is just provide nature with the right environment, and nature has a fantastic way of looking after itself.
Yeah, that's right. Thanks. So Belinda was just wondering if you have commercial compost extract available?
We've been doing trials with that. What we're looking for at the moment is two things. We have a type of a system where what we call is a solid foundation by getting good humified organic matter out there, and then a liquid boost where we can put the liquid humus, effectively nitrogen, out there, but then also top it up with trace elements if needed on the basis of a leaf analysis. We've been doing that work with a couple of select growers. We're just actually now starting to talk to some of our key customers, and we're looking for people who do large areas, like 100 hectares for a customer and so on. So we've probably we're going to set aside a volume of compost to effectively subsidize to enable those customers to take that next step into regenerative farming, and we'll be offering them sort of discounted product. Probably got enough for about 3,000 hectares, I'd say. But if anyone is interested, then certainly just contact us. The liquid compost extract, where we worked on sports turf. You may be aware that WA has a serious issue with sting nematodes in turf, that they're actually destroying turf surfaces, and it gets to the point that some leading sports ovals cannot get to the grand final because it becomes too dangerous for them to play on, because the players may twist ankles and so on. So using that solid foundation and a liquid boost, we've actually demonstrated that we can control sting nematodes biologically, rather than the chemical solution, I think, is $1,500 a hectare and has to be put on twice. We can solve it with no chemicals. So that's just the power of biology. It's just finding the on switch.
It'd be interesting to see that work in, Pratolenchus nematodes or cereal cyst nematodes in a broadacre.
Look, I think the biological principles are the same. So it's not about science or biology. It's about the economics of coming up with a methodology that works for that farming system. And that's where you got to understand that farmer, the equipment that he's got, the farming system is running, and then try and design a system that uses biology as a decision-making tool, not just physics and chemistry, but builds biology. But then the economics have got to work, and that's been hard. It's a really tough. It's a tough game, farming, and I'll tell you what, we compost farming wastes. So if farming's a marginal business, we're a business on the margins of a marginal business. So it's quite tough. Yeah. But it works.
Yeah, great. So Natalie's got a question that maybe, Andy, you might have an opinion, but the two Richards might also, in regards to landholders and extension officers having concerns around organic matter in soils and in increased water repellency, or issues with water repellency.
Oh, that's a good one.
Yeah, is there a good response, references to use to address these concerns?
Do you know when we started doing this 20 years ago, you'll remember Bob Jilks at UWA, and he had students working on the problems with soil organic matter because they caused water repellency. And the analogy I'll draw is let's say you take some shredded garden waste from the council and you put it around as a mulch. When you put it on the surface, and then you go back next year and you say, well, where's it gone? It's vaporized. The carbon compounds have actually gone back to carbon dioxide. And what hasn't vaporized has actually become hydrophobic, because it's the it's that labile carbon that the bugs get busy on, the fungi grow and create this waxy layer, whereas you start with humified product to start with, so that's composted mulches, last longer, and also are less prone to becoming water repellent. So there's something there. There's something that magic of what Richard was talking about, that humified product. It's now, what do you say? It holds 300% of its own weight in water. Well, there's something going on there, but it also can absorb a lot of water. And a humified product is less likely to become water repellent. Now, that's not a total answer, and it's all a matter of degree. Nothing is black and white.
Yeah. So, Richard, Harper, do you have a comment to make? Did you want?
Yeah, we had a student, Mejan, from Bangladesh, and we had him pulling the organic matter out of sandy soils and then re-adding it and to just what we call acid wash sand. It's just basically quartz sand, and they're just sort of straight line relationships. The more organic matter added, the worse the water repellency became, and so it's an issue. And
actually, Richard, I'd love to. Maybe we should come and see you, because some of our customers have got those water repellent gravelly soils, and we'd actually like to modify that liquid extract to maybe deal with that water repellency, and we're not quite sure how to go about that, whether we actually use some wetting agents, or we're just not sure where to go. But we've got customers that want to address that issue.
Yeah, well, if it works, it's great. Yeah, we'll catch up with you, Andy.
Yeah, good.
Yeah.
So Richard, is there a did you then take the next step and say, so that's caused the water repellency? Other than adding wetting agents, was there any other way of bringing those soils back, or was there a maximum amount of organic? You know, we're talking about what's a good amount of organic carbon or a good amount of organic matter. Does a certain amount of organic matter start to cause water repellency, or is it about the type of organic matter that causes it?
Yeah, we tried to look at that, and we're not totally sure. So we've got organic matter from under different plant species, and some plants seem to be cause the problem more, but it's not crystal clear. So we've got another student, and she's doing that, sort of going to different things and looking at the organic matter in a lot of detail, and basically we want to work out whether particular compounds cause the problems. We had an interesting thing with blue gums. We had about 30 or 40 paired plots under blue gums, which had grown for 10 or 15 years, and under pasture. And it was with CSIRO, they'd looking at the change in soil properties. Anyway, we got the soils, and there was no difference in anything between the pairs apart from water repellency. And we absolutely hammered those soils, and we just couldn't find anything that was different, organic matter content or clay content or what have you. And I guess what I was thinking is, if you buy a pair of shoes, suede shoes, and you can go to a shoe shop and you can get stuff you spray on your shoes to stop them being water repellent. I'm just sort of wondering whether there's something similar happening in soils where you've just got a really tiny amount. Like if you weighed your shoes before and after applying the water repellent spray, you'd find no difference. And I'm just sort of wondering whether there's something like that where you've got rogue compounds in very small concentrations which cause big problems. And if it is that, the flip side is I guess you find a technology to seek out and neutralize the those compounds. So it's sort of something we've been pursuing, but not with a great.
And of course, I'm arguing against myself by suggesting that we put in another chemical. But because there's such a lot known about the chemistry of wetting agents, it might be a stepping stone towards where we want to get to. My intuition tells me that if we can get the farming system right, we can actually overcome things, but we can't get there in one go. And I can argue the same with the liquid compost extracts with the, say, 45 with nitrogen. Well, if you get the farming system right, you shouldn't need to add so much nitrogen. However, getting the farming system right may take many years to eventually build up the soil organic matter to a level at which point the 2 to 4% turnover that Richard talked about releases enough nitrogen to feed the plant. But today, we've dropped our soil carbon levels so low that if you try to go cold turkey without adding nitrogen, you'd probably fall over.
Yeah.
And I've an interesting observation on the effect of soil organic matter. That cauliflower crop I talked about, we started with 0.7% soil organic carbon. Now that might be 1.5% organic matter, but 0.7%. We would put compost on every crop. And then after a succession of crops, we built the soil organic carbon to 1.4%. Now you'd have to, intuitively, you'd say double nothing is nothing. So it shouldn't have had an effect, but it made an incredible difference. But we could never get it above 1.5. And that was the point at which we wanted to start working with clays, because I think there is a synergy between compost and clay where we can reach, I think there's a magical point somewhere between 2% and 2.5% where we can optimize production from those coastal sands. But we couldn't quite make it because the rotary hoeing between crops, followed with bright sunshine, followed with irrigation, was all working to break organic matter down. And so we couldn't quite break through that barrier. And I think that work that Richard's doing with clays and compost, I think that could be a breakthrough.
Yep. And there's just a last question about composting every year. I mean, is it the sort of product that you just sort of do a rotation around the farm, a bit like gypsum, or would you, when you're working with your vegetables, are they putting it on every year?
Two schools of thought on that. I actually think it would be more like gypsum, that you rotate every, I don't know, 2, 3, 4, 5 years. We're still learning. But in the first instance, whilst you're kickstarting your soil organic matter, you probably can't afford to put as much on as you need to get to optimize it. So you put on what you can afford and slowly build it up over a period of years. And then once you've got a self-sustaining system, you should be growing your own carbon. If you increase the biomass and grease that carbon pump through using photosynthesis, you should not need to keep buying compost.
Yep.
That's where you want to get to.
Yeah. I guess it's like the analogy that Richard used as in regards to inputs. Inputs in and inputs out and that sort of thing. So you're probably always going to be, you're working with a dynamic system. So you're probably always, if you're taking stuff out, you're always going to put stuff in. But I might just have to wind it up there so you guys get a good break for lunch. So I'm conscious that we've got about 25 minutes and Lynette Abbot will hopefully be joining us at about 1 o'clock. So thank you very much, Andy. I really appreciate your input and thanks for sticking around this morning and listening to Richard and Richard's presentations as well and building them into your presentation. I really appreciate it. If anyone's got any other questions, feel free to pop them in the chat over the lunch break. And thanks to Richard for a few comments at the end there as well. So go and have a break and I'll see you back here at about 1.
All right. Thank you, everyone.
Can everyone who I can see hear me?
Yes. Yeah.
Are they all in? Hello, everybody.
Hopefully they're all there, and we can ask them, Lynn, to unmute themselves if you'd like to generate that discussion. And I'm sure as you start talking.
Yeah, but I just feel like I would like to be interrupted, because I don't just want to be saying things that people don't want to, you know, or that it's obvious or something. So what I, just as an introduction, I took the notes that you gave me, which was a list of the topics to cover, and then I copied and pasted those under three different PowerPoints. So at each PowerPoint, I've got the bit that you sent me about what could be covered as on the front page, and then I'm addressing that. Now, it mightn't be addressed in exactly the way that people might want, because one thing I don't do, and in any context, I really don't do this. I don't say, well, this is what you have to do, or to fight, or this is the way you should do it, or this is the way, these are the steps. And the reason for that is because in my old age, and for many years actually, I just think that this business is about understanding rather than just following a recipe, because every circumstance is different, and it has to be from the basis of where people are and what they want to do with where they're at. So that's why I'm not sort of giving recipes. So the answers mightn't be quite what people were wanting me to say. G'day, Andy. But then that's why if people just interrupt me.
Yeah.
But some of the PowerPoint, it's there for your information rather than, it's sort of there you can go back to. I don't have to spend a lot of time on it. I can be really quick with the slides. And so I'm really wanting to know, it's more important to me what you all want to know. Oh, not that I can answer necessarily, but it's that your feedback into it rather than me just giving you a talk.
Yeah.
Does that sound okay?
Thanks, Lynn.
And I'm happy if everybody undoes their mutes, unless they've got a cat, like I've got a cat climbing around somewhere, and anyway, you understand all that.
Yeah. I have to chew the dog out.
Good. So will I underway? And
yes, please. I'm happy to introduce you, but I feel like you probably know most people here.
Yeah, and I've made a list of names, so when they disappear off my screen, but thank you everybody for having a, so I'm going to just see if this works with the first PowerPoint, which I'm going to share my screen, and then I'll bring up the first one. Now, presumably it'll be that one. And then it'll be this one. Something's not happening. I can't move it. There's some reason. I'll just stop sharing it, and then I'll put it in the middle, and then it should be fine then.
Yeah.
Now let me see. No, that didn't work either. Sorry about this. I don't usually give sharing screens on things at the moment. So share. The problem is I think it's going to share the bit I don't want you to be able to see. Anyway, let's see if this works. No. Sorry, the talk will be over before I start. I just can't get the whole screen to share.
Oh, that's okay.
Does that work?
Yeah.
Okay.
That's.
Oops, I've gone too fast. Okay, so that's going to work. All right.
Yeah, that's great.
Except that you're covering up. I've got the, that's better.
Yeah, you can't see us. That's the problem.
I've got rid of you now. Okay, anyone speak up when you're ready. So this is what I just said I've done. So I've put the soil biology, this is a list that Felicity sent me. And then in this summary, in this PowerPoint, I've addressed this. So, but I'm here listening to your, you can interrupt me and I don't mind that at all. I can't see if you put your hand up because I've just clicked off that so I can see the slides. So I talk a bit about soil biology basics, and for heaven's sake, I'm not going to cover all of that, but some minimal background, and then I'm going to focus a bit more on measuring, monitoring, and that side of things, and then biological indicators. So that's, and there's lots and lots of people who have contributed to all of this, and I just want to make sure that everybody understands this is a joint effort. So you don't need to know this, but soil biological fertility, which is the way I think of soil biology, basically it's contributing to the fertility of the soil in a broader sense. And so how do you unpick the biological fertility part of it? And this is the first animation. I'll see if this works.
One of the biggest challenges for land managers is to ensure they take advantage of the beneficial biological processes in the soil and minimise the detrimental ones. Soil fertility reflects the physical, chemical and biological state of the soil. Soil biological fertility is a key component of soil fertility. Knowing the origin of soil helps to predict its fertility. Soil management alters its fertility, and assessing that fertility is no simple process. Soil contains an immense diversity of organisms, and many of them can't be identified easily. Bacteria and fungi can now be identified using new molecular biology techniques. Soil animals can be extracted using sieving or heating techniques. Soil is a diverse habitat. Soil type dictates the microsites where soil organisms live. The diverse community of soil organisms is dynamic and interacts with both physical and chemical components of the habitat. Organisms that live deep below the soil surface don't rely on plant organic matter to survive. The activities of soil organisms have important links to many soil processes. Autotrophic organisms transform inorganic molecules to obtain their energy. Heterotrophic organisms obtain energy from organic matter. The release of CO2, enzyme activity, growth and reproduction are examples of microbial activity in soil. The amount of CO2 released by microbial activity in soil is generally related to the abundance of organisms, but some may respire at a higher rate in harsh environments than in less severe conditions.
So that's the first of 7 animations. And these animations relate to the book I wrote that was on the web for many years, but it's being updated. It's not on the web anymore. And that will be available in not too long distance. So soil health is flavour of the month. It wasn't when I started working in this area. And there's chemical, physical, biological components. And so when you think, well, what are the components of soil health and what do you measure and what can be used as an indicator? I think I go to this website, it's called Soil Health, the Soil Health Institute in the US, and it's a pretty good outfit, and they have looked at measures of soil health, and this list is the ones that they say are really robust. You can measure these, and they're not really biological. So they're happy with the non-biological things mainly, although soil carbon is, of course. And they're really waiting until the biological tests are sitting there waiting because nobody's absolutely certain about them. Or at this stage, it's a little bit old. It's a couple of years old now, but still, when I went to the website today and it hasn't been updated really. So when they go, in this case, to the soil, to the more biological indicators, there's a list here, and I'm not going to go through all of them, but there are many biological measurements that can be made. But I think the fact that there's so many different things can be measured, that's the whole point of the confusion in this space. And I'll come back to that later. But this is where they're up to, and this is data from, was put up as of 2018, but there's nothing updated on their site, which is pretty an active site. Then if you go to the soil quality website, I think there's a lot of really good information there, and they list biological measurements and potentially as indicators, but that's a bit of a question what an indicator is. I'll also mention that in a minute. So that is a very good website with a lot of useful information. And Richard's already given you some background, probably that covered some of that stuff today. So the point about this work that was done in the WA context, the idea was what's a good level and what's a bad level or not so good level. And so I think this is a really important point, because you can have a soil with a certain amount of something in it, and that something might actually be very good for that soil. But if the same amount is in another soil, it might be not very good. So in that broad non-scientific sense. So just measuring the amount of something isn't really going to tell you, especially for the biological measures. So measuring something and then understanding what the measurement means is there's like a chasm between the two. And that's why I think it's about understanding and then making decisions that are locally based. So in terms of the biological measures, things that you need to come to, and this is a common theme, I haven't, what are the principles involved? And in this case, you know, time, things take a long time to develop, especially if they're biological. Then you can have nutrient replacement. You can have scheduling of nutrient supply can be important in some situations. And this impacts on plant physiology, on the production of the product, the quality of the product, and of course the cost. So this is sort of all about, so you can measure something, but then to get it into something that's practical or use it in a practical way that has an economic benefit for the farmer or sustainability, you know, the links between these are not very, they're a bit wobbly, and I think that's important to keep an eye on. So in terms of soil biology tests, there's a lot of stuff out there. You can measure a lot of things. Ongoing, there are new tests available. But I like to think of it, soil biology tests in this way, that some are just for researchers. So there are some biological tests that are not useful for the broader community. They are to understand in scientific experiments something that's going on, looking at a mechanism for why this happens or why it doesn't happen. And then, so that's one lot. Then you've got off-farm biological tests where you can send a test off to somewhere and they can do a measurement for you. So that's not necessary research, that might be for monitoring. And then you've got on-farm measurements. So there are things that can be done on the farm that are much perhaps more simple, but they might be just as effective for working out in a practical sense for sustainability in the location. So those 3 points, whether they're for research, and often they're complicated and they're expensive, or they're technical and we don't have the facilities on the farm to do them. So this is a few examples of tests, and these are related to just measuring what is there. So the occurrence of something, so microbial biomass or particular organisms. So this is also important. So you're measuring, in this case, something that is there. Now, that doesn't say that that is a good or bad thing or useless or helpful, whatever. And then there are other biological tests that measure an activity. So something that's doing something, so soil respiration, and these sort of measurements have a different flavour to these ones which just measure that something's there or not there. This measures something that those that are there might be doing. And you might also note here that this activity could be related to the activities of groups of organisms, not specific organisms. So more than one group might be doing the activity. And then my next point, which I think is still very important, it's ancient history for me, but what do you sample? When do you sample it? Where do you sample it? How many samples and how often? All depend on things like the question, what you answer, what you want to know, what you want to do, and when to sample. What are the seasonal effects? You know, within a season, between seasons. It might have no use to anybody to sample at a particular time. And then how variable is the site? And then how many samples you take depends on the variability of the test. And so a couple of samples might be quite useless as for a lot of the biological tests. And then how often? Well, again, are you monitoring yearly or seasonally? And these are very important questions, because if you sample at a particular time, that time has to be relevant to the type of question you're asking and the analysis you're doing and all of those things. So this seems like it's really basic, but it is almost the key thing, because if you measure things that are, you might be able to measure something very complicated, but if it has no relevance to the timing, or it might be very variable, so you measure it the next day, it's different. So I'm really focused on this aspect, and a lot of people sampling probably don't have as much attention to this as is needed. So I think I've got a little cross on here. Get rid of that. So this is the same about what I've just been saying, basically. It's about how you take a sample. So how do you store the sample? How do you send them? If they're biological samples, if you take a sample and put it in an envelope and send it over to another company somewhere, what are they seeing compared to what was in the soil? And then this whole question about what does a soil test indicate? So we often talk about indicators, but really we only mean what are we measuring? It's a measurement, it's really not necessarily an indicator. And I think every time we measure something, the question then becomes what does it indicate? And that connection is rarely done. It's usually that we're just monitoring something, but we really don't have an indication of what it might do. And the question you can ask around a soil test is, can it be used to predict something? So prediction and indicate are sort of together. And if it's just a measurement without any capacity to indicate or to predict, then it's not probably so useful. Ah, where have I gone? Here we go. So a lot of people have argued about all of these biological tests for a long time. And there are some conceptual issues with biological tests, and there are some practical issues. So conceptually, historically, there've been a lot of arguments about what is soil health. And I think we've got over that a bit now, because we actually talk about soil health now, which we didn't used to. We need to know what the baseline is, because often a soil test will mean nothing relevant unless it's related to some kind of a baseline. And that often depends on what's the soil, what's the origin, what's the location and environment. And then this idea, this concept about the five-year turnover, if something takes more than 5 years to change, takes more than 5 years to measure a change, then it's probably not a very useful test of anything. So some tests might not be able to pick up a change in a biological component within a long time, and therefore it's probably not very useful. But mostly we're interested in how management changes the measurements that we make, and that's probably the monitoring is the most important thing. Whoops. So when you get to practical difficulties, there are a lot of issues with the sampling. And this is my overall point about this last thing. In a way, despite what I've just said, within that framework, if you pick some tests and then you decide on what you're going to do and you just consistently use those tests and look at how they change, that's probably more important than going into a lot of details about complex tests. So I would say be consistent, just make a decision, monitor over time, and don't worry about all the millions of things that you could be measuring. So, but sampling is very, very important. And what you might need to do in different soil zones or climate zones or whatever might be not the same. So there's no recipe that's absolute around these things. And then researchers and farmers might have different needs, and then I've just addressed that. Now, I'll stop for a minute because the next bit is just some example. Does anyone have any questions so far? Have you been able to hear me?
Yes, that's been great, Lynn. Freya was just wondering if you'd be able to, if we might be able to get a copy of your presentation.
Oh, absolutely. Yeah, this will be, I'll just forward this to you, Felicity, at the end. And no, definitely, that's sure.
So if anyone has a question, please unmute yourself or type something in the chat. But there's nothing in the chat at the moment. But if someone wants to ask, then unmute yourself.
Perhaps I could ask a question. Lynn, you talked about 5 years as being sort of a time frame, and if we can't see a difference within 5 years, it's probably not going to be a very sensitive indicator. Soil organic matter is sort of on the borderline of 5 years, and that's already taken to be quite an important property of soils to measure.
Yeah. Well, that 5 year work was actually something that Newey Milton did when she was working with Dan, and we didn't ever publish it as a proper formal paper. It was in a conference, but it's just it might not be 5 years, mightn't be the crucial thing for everything, but the idea around it was that if something takes a long time to measure, and maybe soil carbon comes out of this list, it probably relates more to, you know, if you're measuring a specific group or a particular, you know, like microbial biomass, or even measuring things like pH, anything that is taking a long time isn't going to be a useful indicator as you go through time, if you know what I mean. So, but I think it comes back to this other point, and that is if you understand how long things take to change, and as we go forward, we will know more about that. So as we understand more about how long it takes to build up organic carbon in soil, for example, carbon, then we'll know more of how long to expect. And it's understanding that's the more important. So I think this point is really just not to measure things at random just to measure them, but to understand why you're measuring it. And in this case, it's if they're not going to change much, they're not going to be much of an indicator. But I understand the point about the carbon, and you know but again, the measuring of soil carbon is a complex thing, of course, you know, and that sometimes the carbon might not change in a 5-year period, but components of it, like microbial biomass, might change in that time, or that the turnover of the carbon there might be slow or fast. So the reason it's staying the same might not be the same reason. So you might have the same amount, but it might have got there through rapid turnover, and it's staying put, but in one case it's turning over slowly, in another case it's turning over fast. But where it's turning over fast might be more beneficial, even though the total amount is the same. So that's why understanding is really all part of this. That was a long-winded answer.
Yeah, I have that summary table of Newey Milton's work, and I can't even remember where I got it from, but
it's been in lots of talks and
I got a hold of it, and I actually use it when I'm talking about monitoring soils.
I'll tell you where it was. It was actually, it came from a specific research experiment by someone in the Department of Agriculture, and I'll remember his name in a minute. Hamilton. It was, it might, yeah, anyway, it was from a grey clay trial that was done in the south part of the state. Greg, yeah. So that was where it was done. And so it was actually done at a site, testing all these things and predicting how long they would take to change. So it wasn't a sort of a broad scale study. And it might be a bit different in other sites.
Lynn, I've got a quick question just on that, on the soil carbon, and I guess the time frame, which probably could have brought up earlier, but you know, there's a pastoralist over in New South Wales who has now got a, you know, selling carbon credits, I think, to Microsoft, and he seems to be on very good soils, basalt soils, and perhaps his soil carbon levels were very low for those types of soils, because I think he started at about 2%, and now they're up at, so he says, up at 4.5%. I'm not sure exactly how he's monitoring, but you know, you hear quite often that it takes a long time to build up, but then you hear examples like that. Admittedly, nothing's ever been published and it's really just hearsay, but you know, what are we to sort of think of those media? Yeah.
Well, I mean, but again, as we get back to understanding a site, so you've said this is probably a fairly fertile site. So it also depends on the history of management of a site. So you can have a site which has been, you know, maybe just cropped continually, and then another site on the same soil that's been rotated with pastures, or, you know, the opposite in a way. And so, you know, understand, if you know what the management relationship between management and the measurements are, then you can make predictions, and you'd certainly think if it had a history of depleting the carbon over time or keeping it at a low level, and then you suddenly change it to make it accumulate. And that could happen faster, of course, on a heavier clay soil with a lot of water around and a lot of roots and plants. So, you know, I think you can almost predict a lot of these things by just understanding the mechanisms of how things work, and then compare it with what you can measure.
Yep.
Just adding to that, we're doing work in Bangladesh where they grow 3 crops a year, and we're able to measure changes in soil carbon in sort of 2.5 years, which is 7 or 8 crops. So obviously here in Western Australia, you need 7 or 8 years to be able to get through that many crops, and probably the total biomass that you produce would still be lower.
Yes, you're right. True.
The best result we got was under Takasasti. I think it had grown for 20 odd years, and that was 3.5 tonnes per hectare per year of soil CO2 equivalent. So it's not C, but CO2 equivalent. Which is what
And that would have had other pasture plants on the ground under the Takasasti? Wouldn't have been bare ground under the Takasasti?
Under the Takasasti, it was just a closed canopy, but the adjacent...
But would anything be growing underneath it, like on the ground under the plants? There'd be just,
no.
oh.
Sometimes it's not. Sometimes it's that close together that there isn't.
Yeah.
Okay, yeah.
But,
I mean, that would have an effect too.
Yeah, I think what happened there though was the baseline was the adjacent land was capeweed and not much else, and you know, it was basically pretty hopeless and probably been knocked down. So in that case, it was sort of starting from quite a poor baseline, and you put something that's growing quite vigorously, and you get a bit of action. But we had another site where I think trees, they're old Eric Greenwood's CSIRO trials out in the wheat belt with trees, and they were 26 years old, and we compared under trees, which grown quite well, with adjacent pasture, and there was no change. And there's been a couple of other sites, and I guess my takeaway is if you start with something that's pretty hopeless, and then you put something that grows much better, you're gonna get action. But if you're comparing something that's productive with something else that's productive, probably you're not going to get a bit much of a change.
Well, that's another point that I wanted to make today about local and understanding that it's so different across the whole of Australia, even within Western Australia. So looking at the patch of land you're talking about, I mean, that mightn't be the issue you're interested in. It might be broad scale, but you know, how do you get this patch of land to be improved? Then you have to sort of relate it back to what you've got in front of you and what history it might have had. So how are we going? Anybody else want to? I'll just flick to this. I've just got a couple of comments here about, this is some data we did with Andy actually, that was looking at the long-term effects of compost on a sandy soil. And in this case, it was carrots. And this is about measurement. So here's a site where the compost had been added or not. And then there was a benefit of the compost in this case. And then we measured mycorrhizas. And I just wanted to mention mycorrhizas here because you can go and buy mycorrhizal fungi in a bag and throw them out. We measured them here. But what I wouldn't want to say is just because we measured that there was an increase in mycorrhiza, that was having a benefit in this system. So that, without going into detail, is, if you can measure something, it might increase, but it mightn't be relevant. So because it depends on what you're measuring, when you're measuring it, and whether it's actually functioning. So that's a sort of a measurement thing. And they've got this other study we did with South West Catchments Council, Peter, which is still really helpful study. And in this case, we measured, we looked at not just a measurement of a whole lot of soil biology measurements. We did some DNA measurements, and we didn't just compare phyla changes in these. We actually went into the DNA and worked out what the functional genes that related to carbon and nitrogen were. And so we were trying to dig into the DNA data to see whether you could relate the abundance of genes related to function in relation to the management. So I'm not going to talk about that further, but I'm just saying there's layers and layers here. And these are a few examples that we've been doing. And one of the things, and it's in the blue at the bottom, it basically that the soil biological processes that involve carbon and cycling nitrogen can change without a change in the chemical tests. So you might get no change in a lot of the chemical tests for a lot of these things, but there could be still things going on at a functional level underneath in there. So it's just an excuse for looking deeper, that's all. So what I've just done here, and we won't need to deal with this, but I've thought, what are your summary points that you want to put? And there are not many probably from what I've just said, but there's probably some key points which I've just left there for you to do if you want. So that was the first one. And that, if I go back to the, I have to get to the top now. Get to the top of it. I've just undone it. Anyway, I can't get back to the first one. Maybe I can do it this way. I mean, that was, the aim of that was to look at biology basics, which obviously I can't spend a lot of time on, but then measuring and monitoring. So at the end of the day, I say, there's no simple recipe for the indicator, but it all links back to the management and the monitoring. So that was sort of my attempt at the first set of questions. So we're going okay?
Great, Lynn. Thanks. Yeah.
All right. And I'm available to later. I mean, this is a very short time, but I'm able to come back, you know, if you've got any questions later. Now, this next one, I'll leave it all up like this because I'm not going to probably talk to you on every aspect of this, but this was about soil amendments, inputs on soil biology. Now, this is a really common question that people want to know how agricultural inputs affect soil biology. And then that's connected to this other bigger question, creating and increasing biology. Right. Now, again, so the two questions. And then this is, if you just think quickly about soil amendments and what are we putting onto soil to make plants grow? And basically we've got fertilizers, and we've got fertilizers of different solubility and lots of different kinds of fertilizers and different kinds of nutrients. So I just put that in a big bundle and put that aside for a minute. Then you've got lots of different herbicides. You've got insecticides and fungicides. Some of the fungicides go onto seed, and that means that they're present when roots start to grow, and that has an implication for biology. Then you've got this big broad band of biological amendments, and some of these are actual living amendments, living biological, and some of them are just extracts, so like biochar or humates and things. So that's a general, they've got carbon in them basically. And then you can amend soil by growing plants in them. So you can grow different plants and they'll have different effects. And Richard already alluded to growing plants and how that affect or didn't affect. So that's my big sort of summary picture. And now I'm going to tell you what I'm not going to talk about, because to be honest, there's huge amounts of information about this fertilizer had this effect and that fertilizer had that effect. And then the same applies for herbicides and insecticides and fungicides. So let me just bundle that up in one quick comment. So that's the top pale blue section. So you can add all these things and they can actually help plants to grow. So a lot of people think, oh, we don't want to add fertilizers or we don't want to add herbicides or all of this. So let's say by adding these things, you actually get more biomass, and consequently you can actually have more biological activity in the soil in association with these bigger plant masses. So saying one thing around this, that saying, you know, you shouldn't add fertilizer or you shouldn't do this, then if you put that in the same sentence as how that affects biology, then sometimes it obviously can have an effect. It can change the diversity of organisms. It can do a lot of things, but often it can increase microbial biomass because you've got more plant matter, because you've added more fertilizer. So you've got more roots, so this simple question is very complicated. So what's the effect of these things on biology? It also then comes back to being quite local. So you've got to ask the questions locally rather than in this broad picture. So especially when people say with mycorrhizas, which I do know a lot about, and they say, oh, well, we've got to add some, we haven't got enough in there. You know, that is just showing a lack of understanding, because why haven't you got a lot there? Or what's the context of these things in relation to function? So while I'm happy to say that all of these amendments can affect the biology of soil, there's a whole question about whether it's affecting it in a negative way or a positive way. And obviously, under some circumstances, excess of anything will cause a problem. And so if you put too much of anything on, it will probably cause an imbalance in the system. So I'm sorry, I'm just going to bundle that up in one, but it just depends what you're using and where you're using it and what the soil is like and everything in the environment. So but just keep in mind when we're investigating this sort of a question of what are the effects of these things on soil biology, it's not necessarily a negative effect. It can actually be an increase. Whether that's an increase is a good or bad thing, that's another question. So having more of something doesn't mean it's better, for example. But a lot of these measurements, if you've got more biomass of plant matter, then you're likely to have more biological something. It could be biomass or it could be other things. So then when the next thing I've got in this list is biological amendments, and as I said, they could be active or not. Now, we did a big study with GRDC that I'll give you all the details of that in a minute, but the next lot of slides, which I won't have time to go through each one, but this is a summary of that paper. So we did a review on soil biological amendments, and then there was a document, the report written for GRDC, and I've got the link here to that website, so you can have a look at that. So here we're really talking about this big broad picture of inputs that don't include those factors above that I've just mentioned. So let me just see where I am here. Now, I like to start with this sort of a discussion here where there's a history of use of amendments, and including biological amendments. And then in the old days, a lot of amendments before the fertilizer industry was, the amendments were biological. And then we moved into the industrial fertilizers and then the inoculant industry. And then we moved into these integration where we use combinations of things. And then now we're in a very interesting situation where we're in the marketplace. So we're selling biology now. And so this is why I think understanding soil biology now is really important, because I went on a website accidentally the other day and they were selling mycorrhizal inoculum. And there were so many things wrong with that site, and it was a commercial site. So the people who were selling this product didn't really understand enough. So I think we are now in a situation where soil biology is important for sustainable practice, maybe, but it's also important that farmers understand it, because they can be susceptible to purchasing biology. So, and if they don't understand enough about the biology they're purchasing, then this can be a problem. So, I mean, this is a general point I'm making, but it really means that understanding biology is important in a broader sense than just to try and incorporate it more in agricultural practice. So then I've just got a summary of this, what's in this paper, and it was done with CSIRO, so a lot of people involved. But it basically looked at the substances that are inert, well, not inert, but not living. And then, so that is available now. A lot of you mightn't be able to get it off the web, but I'm sure it'll be made available to you if you can. So that's a review, and that was published in 2018. And then the report that went to the Grains Research and Development Corporation that's the website for that. So that's available. And that's really where we think that's at. And that includes what do these things do? And the important thing to remember that these amendments can have direct and indirect effects, long and short-term effects, and they can affect biology, chemistry, physics. And often when you start looking at these biological amendments overcoming soil constraints, they can have wide-ranging effects, and the same product can affect all of its constraints. So it's a very interesting way that biology actually influences some of this. So a lot of these effects are related to biology. Now that wasn't the question that I think I was asked here. It's sort of what is the effect of amendments on soil biology? But I've actually tipped it on its head and said, what are the effect of, what have I done? What are the effect of the biology on soil constraints, which is a slightly different way of looking at it. But I think this is, the way I think is about understanding it. So if you understand this, then you can look at the question of how the amendments will affect the biology, because all of these organisms, that you just can't look at every one singly. You've got to look at it collectively. So in some cases, like disease, you will have a particular organism, or if the nodulation doesn't work, you're looking at a particular organism. But often you're looking at groups of biology that are affected. Now, in this case, we're turning it on its head and saying, how do these amendments influence the biology to have a better effect? And so that's what this story is about. So I think if you've got any questions about this paper, you can get back to me, but that's just a summary. And interestingly, some of the same products have an influence on the different components of soil fertility, not just the biological components. Now, of course, some of these components will provide a nutrient source, but that they might complement fertilizer inputs. And then, so, when you're looking at trying to eliminate a fertilizer, that's a whole different question, because, my view is this isn't about eliminating fertilizers, it's about complementing and only adding the amount of fertilizer that you need in relation to what all of these organisms can do in response to other soil amendments. So you're going to influence the environment of microbes to make them work better and complement other inputs. I suppose that's the way I could say that. That's a physical. So the biological component of the soil has these impacts on physical fertility as well. Now, just a quick comment about inocular. And while, inocular for rhizobia are unbelievably beneficial, there are lots of microbial inoculants that are not necessarily. And one of them is mycorrhizal inoculum that we wouldn't really recommend. And we've made a couple of, I've got this as in press, but it actually was published in 2017. I didn't put the date, the publication there, but this is becoming a big issue, and more people are trying to sell mycorrhizal inoculum. And we in this paper have explained why that's probably not necessary or could be detrimental. So that's just an aside. And now I want to just talk briefly about a timeline. So if you put all of this into where you are in management, so someone was doing something in a soil that had been quite severely degraded initially, then what you add and what you're trying to do in building up fertility, the biological fertility in that point might be quite different to something that's already pretty good. So I like to think that you might be doing different things along the timeline, and the timeline will also change as climate changes. So especially if you're looking at water related issues. So timeline is important, not just at one point, and where you are for a particular site, it has a transition from maybe being not so good to being really good. And then you need to try and work out where it is. And then what you do along that timeline might be different depending on where you are along it. So this is pretty vague, but it's really important as well, because if you go buy an inoculum off the shelf for something, apart from it might be rhizobium, which is different, buy this microbial product that you want, it just mightn't work at a particular phase in this timeline. So that's just another point to raise. And there are a whole lot of quality control issues around products. So some of them are not well controlled. So that's the other point. So that was, I'm just looking at the time. So that's the end of that second one.
Lynn, we have got a question here, and your point around you know, people selling biological amendments. So yeah, the people in the audience. So Freya Spencer from Gillamai, a grower group. You know, these grower groups get approached by companies, you know, asking them to do independent research on their behalf and those sort of things. So what sort of advice can you give these guys to sort of weed out what might be worthwhile to be exploring and others that are not so worthwhile?
Well, I'm really keen about the idea of testing and doing trials, you know, and even unreplicated trials. I'm a scientist, but don't hit me over the head with that one. But I think, you know, there's a lot you can learn on farm. And in the paper that I've been talking about, which is the 2018 review, we actually write about this point at the end about, you know, testing things. And so, you know, if you do it well, so it's just, there's so many products, they can't all be tested, but there's a procedure for testing things well. And if the people that you're dealing with are prepared to do it well, I mean, I do know in this historically where people haven't been happy about testing them thoroughly, you know, and that's just ad hoc things that happened over the years. But I think if people are prepared to give it a good test, then it's very worthwhile, you know, and it's just doing it well. It's so, because nothing, it's worse to do something poorly and then at the end of the day you get nothing. So do it well, monitor, understand it, you know, have it in the context of what do you expect will happen, and don't be worried if nothing happens, because that can also be part of a good answer, because it mightn't happen this time, but it might happen next time, and it might be just the year that it doesn't work. So yeah, I would say I would, you know, but then you choose who you want to work with, really, apart from, you know, there's kinds of products that are relevant to the local area. But yes, you do give some guidelines in that paper.
Oh, good. So guidelines is good, because I think that's important, like understanding what it is that product, the hypothesis around that product, you know, what is the expectation, you know, is it an increase in yield? Is it an increase in root growth? Is it an increase in soil biology that then results in increased nutrient cycling? I guess understanding what it is that you're expecting, you know, what outcome are you expecting, and making sure that you understand what is it that you need to measure to be able to determine if that has had that outcome, you know.
And the other issue is that the effects might not happen in a year. You know, that's the other problem, that it might not even be easy to test it. So often these changes occur slowly. And so, you know, just because you don't get an effect in 1 year, and some of the products are meant only for 1 year. So that's the other thing, that some of them are not meant to be ongoing or whatever. They're just a single short-term effect that might be the one you're looking for. So it's just going into these things with a rigorous thinking, that, and then monitoring and learning. I mean, you can learn from, in fact, I think in my career, I've often learned more from things which went wrong. So if you can't predict the outcome, then there's more you need to know. So, but you know, often there won't be an effect, and I don't want to dismiss a product that doesn't have an effect, but they're learning about how you did it and whether, you know, you might have, something might have happened and it didn't work properly. But there's a lot of things out there that are put in bottles that probably won't work. And I could say, you know, that's the case for some things, and you could work that out before you start.
Yeah. So how do you work that out before you start? Is there any regulatory bodies that?
Well, I think it's interesting. There's a group I bumped into in another state once, and these people had a product and they really wanted to, they liked this product. They said it was very good, but they wouldn't make the data available about the product. And then the other problem can be if people do present data, whether you can look at it and say, well, no, I don't really follow how this was done. And so you can look at what evidence they give. And if it's just a marketing exercise, then you've got to look at it in a bit more detail, talk to the people who know about it. So there's a lot of good stuff out there, and it's just a matter of weeding out some of it. And there's so many things now that understanding is the key. And then you make a sensible decision about what you might check. But some of these tests need to be, if they're long-term effects, they need to be done over a long period of time, and that's often difficult. That mightn't have helped you too much. I've just got one quick thing in this final presentation. I think I've got 1 minute left. Can I have open this one? Because there's only a couple of slides here. This one was related to the question of regeneration. So I think I've addressed this as I've gone a bit about how do you get the biology working again. But the key to me is what was the soil originally like? And so the soils in WA were not meant to grow wheat plants or clover plants or anything really agriculturally in that sense. So you can't just say we want to put the soil back to like it used to be. And that's a common comment. We want the soil to be like it used to be. Now, in often cases, there's more carbon in the original soil, and so that's good, but there's not much other. So that's one question. You can't go back to the original. You go back, we want to know what it was like, where it's come to, and then we want to say, what do we want to grow in this soil and what do we need the soil to look like? And so the idea of taking it back to what it was originally is just not part of this, because in WA, we couldn't have grown things. So what do we want to use and what kind of environment we want? So just a couple of points here, that what was originally like, what do we want to do? And then understanding the principles of biological fertility is then the key to the next step. So I've listed some principles, and in the book that I took off the web, which we're working on to publish, I have 10 principles, and basically they're around these sort of questions. And for each of these principles, there's a related soil management practice or series of practices. So this is why I'm going to finish off by talking about principles and understanding, and not following a recipe. Once you decide what you're going to do, you can follow a recipe, but you have to, you have to decide what you want to do. And if you want to measure certain things, that's fine, as long as you're consistent and do it logically over time. And then I'm not going to show this animation, but this is the final of the animations. And as we've talked at the beginning, Peter's got the animations, so he'll send you the link. And then so that's why I've tied that up. And so there's nothing much in that one, but it was just that main point in this last PowerPoint about principles. And so, yeah, that's...
Thanks, Lynn. Yeah, Peter provided the link to those animations, so we'll be able to go back and have a look at those. So.
Okay, and I will send the 3 PowerPoints to you. Now, the problem, because the animations will be too big, so I'll probably have to take them out. I'll send them to you as PDFs, and then the animations are available separately. And then the other thing is that I'll add that other reference that I missed out on in there.
Oh, great.
So, gee, that was pretty fast and probably not.
Fantastic.
No, I didn't answer all the questions that everybody had, but anyway.
No, you've given us a great overview, Lynn, and I really appreciate the way that you've presented it as thought-provoking and sensible, really. So, but I'd like to open it. I know we've got our time. We are up to our time, but if anyone has to go, I completely understand. But I don't want to cut it short. If anyone's got any burning questions for Lynn, please unmute yourself and ask away.
I might just say before that we do have this Landcare grant, which we're making a soil health app. And so that grant will finish in October, but we'll have it probably done before. The app's been made and we're just waiting for the podcast to go on it. So that'll have the animations, it'll have a little booklet about key points, some of which I've talked today, and it'll have about a pile of quite a lot of podcasts of me reading the book. So it'll be related to, and the book's been structured around developing understanding of soil biology. And so that will be the app, that'll be free. It'll, then separately, we're going to publish the book, and the book will be available for purchase online. And we're just trying to make it as cheap as we can. We're not going to have a lot of pictures. There's a lot of evidence, there's a lot of data in it, but not a lot of pictures. And I just might alert you to the fact that you might have seen it, but on Soil Day in December, they released a beautiful book on soil biology, soil biodiversity. It's massive book. It's available for download. It's a huge document, but it is just all the beautiful pictures of soil organisms doing their thing. And so our book doesn't need any pictures because we can just refer to that. But that is something well worth downloading. It's free. And if you just put soil biodiversity, it probably comes up. Yeah. It's recent and it's fantastic, beautiful.
Is it on the world?
Look, it came out with a biodiversity group, but it's a group, they have already done an atlas of world biodiversity, but this is a new one. It's just come out and it's astounding. It's unbelievable. Wow. And it's a lot of knowledge in it. It's not just pictures, but it's absolutely, if you can't find it, I'll find the link to it, but it takes a long time to download because it's very big and you can't just send it around, or you can if you can sometimes with these magic ways now, but it's huge as a file, so it's best if you just get your own.
Okay, is there any questions?
No questions?
No questions?
I'm happy for people to come back on any of these points too, individually, like I'm happy to talk to people or write something. It's easier to talk than to write. Yeah. And when the book's written, I'll just send you the book.
That's right.
Or the link.
Thank you very much, Lynn. I really appreciate that you've
Andy's got a comment.
Yeah, he's got a comment. Yeah.
I've just an observation. I believe I know the farm that Lynn showed slides from carrots. The grower there was saying that's the one where they use compost regularly. We're saying they actually could use a higher gear in the tractor when they were tilling the soil, because the physical properties of the soil changed enough they didn't need to use as much horsepower. Now that particular site, they stopped using compost, and I went back 5 years later, and they said they still didn't have to, they could still run in a higher gear, which supports what Richard was saying earlier, that the humus fraction of soil carbon is quite persistent in the soil.
That's good.
I was just going to ask quickly about strategic tillage and like one-off sort of tillage for water repellency and that sort of thing.
Mm-hmm.
And in the process, turning over that organic layer and burying that a bit deeper into the subsoil, could that, number one, I guess, is, how much would that, a strategic tillage affect carbon and biology? And number two, could we actually improve soil carbon if we're burying that, topsoil in, at the 20 or 30 centimetre, and we can sort of rebuild just on the surface, with our crop residues?
Well, there's a different reason for strategic tillage, of course, and that's not related directly to those, because if you think of the organisms in soil as a community, then a level of disturbance is important. So some level, I'm not saying how much, but just some level of disturbance. So if you completely don't disturb it, and you might say, well, a forest is, you don't disturb it, but actually there's enough organisms in that soil to be doing equivalent of disturbance. So a forest soil would be quite disturbed in that sense, compared to just an untilled agricultural soil that's had heavy traffic over it. So biological fertility, biological diversity will increase. Well, you can maintain it at a higher level if you have some disturbance. So there's a value in disturbance. But the second point you made about burying it. So then you can think, well, what happens when you bury the soil? So you're burying it, and then, so some of the organisms, you might have less oxygen at depth or something. So you're going to change the habitat for organisms if you put them at depth. And in fact, what you might do is change it so that it doesn't break down as fast. I mean, that's one, you could think of what are the options. It might break down fast because you've disturbed it, and so that you've added. So these things are, we've just done a study, it's probably a year or so now, with David Hall in the department down at Esperance. And we had a student who looked at the burying of organic matter with his different tillage practices. And we've got a lot of biological data on that. It's being written up now. Hopefully we'll get it out fairly soon. But, I think some disturbance is good, but the more you disturb, the more you'll burn off the organic matter. So that's one issue. Disturbance creates diversity because you're not getting a stuck system. And then burying at depth, it's more of a Richard Harper question with the depth. But if you think of it in terms of what is that organic matter going to do when it goes to depth, I mean, it depends on what kind of environment it is, how fast that will break down, and it might just sit there. In fact, if we looked at the site over in Esperance, where the organic matter was buried, and it was 5 years prior, you could just see the layers where it went, because in that situation, it was a white sand, like beautiful white sand. And so the organic matter was very visible because they made transects down, profiles, and they sampled against that sheet. And you just could see where the it was still there. So, I mean, that's not a quantitative answer to you, but you could see where it was buried, it was just still sitting there. Now, that's at that site, which is not a very, fertile site with a white sand. But anyway, so, I always go back to what a gardener would do about burying. And, that's the extreme, what you do in a garden. And then you try to translate that out. And then you start to shed what's possible as you go out into the broadacre. So, yeah. But Richard, are you still there?
Yeah.
What's the story about burying organic matter and building carbon by doing that?
I was just trying to think. I think Susan Orgill over east in New South Wales, she buried bits of cotton at different depths. I don't know whether she's written that up. There's a lady at ANU did the the same. And I know at a seminar we had a bright idea: we get carbon credits if we encourage people to be buried at 12 feet instead of 6 feet. It's probably an idea that was going nowhere, but yeah, we measured carbon down to 35 metres under pasture. It was old carbon from pre-clearing, 37 metres, I think. And there's sort of small amounts all the way down, 0.1, 0.01, 0.02%. But if you totted it up over that distance, it was, I think, 2 to 5 times more than you'd normally expect. But the key question to me was, could you change land use and store more carbon down there? And I think that's unknown. There's a little bit of stuff done in the Amazon where they're comparing rainforest and deep-rooted pastures and trying to get more carbon down at depth. But yeah, I think it's possible, but that's a little bit different to burying it. I think the general idea was the deeper the in the soil, the carbon, the less biological activity and the more resistant it's going to be. Sorry, I was a little bit rambly, but
no, but I think it shows that, you know, that there's not simple answers to some of these comments, I think, questions. But it's good to ask the question, because then that sets the path to see if there's a simple answer or a complex answer. And that's why I think I'd like to come back to what's the actual location and what can you apply there. And, you know, I mean, I worked on mycorrhizas for decades, and I always thought that just understanding what's going on was enough, not the measurement of it. So understanding, and then you could predict what would happen with different management practices. And so I think that same thing can happen in any of this area, that you can actually predict. And the other thing is that there are not a lot of options for management anyway. And so, you know, and you only get one chance a year, or unless you're in Bangladesh, you get 3 a year or whatever. Anyway, that's a ramble too.
Lynn would, Rich probably know, but if you cultivate soil, so if you're cultivating to bury, you're likely to, through the cultivation, you're likely to mineralise organic matter. So the process alone is going to result in a loss. But I guess if you counterbalance that by having it at depth, maybe that's better. I know Fran Hoyle said in a couple of her papers that a lot of the soils are close to capacity in terms of soil carbon storage. And
that's the surface of them.
Yeah, and so she suggested that if you can get it deeper, you know, obviously you can store more, and it sounds reasonable.
Depending on what the bugs are doing down there, though, like
and then you relate, well, what's the habitat like, and that'll affect their activity. So it might be more hostile as they go down, and so anyway.
So I could just add something there. Been a lot of international comparisons on soil carbon between conservation ag or no-till compared to full tillage. And of course, the prediction was that no-till would have an increase in soil carbon. But actually, the evidence is pretty slender in that regard. It often shows not much difference. And but it's changed the distribution of the carbon. So under no-till, there's more at the surface, but there's actually less in the subsurface. Whereas in the tilled situation, there's not as much concentrated at the surface, but there's more buried deeper. So I guess that is suggesting that the faster oxidation that's occurring with the tillage is being counteracted or offset to some extent by the burial, which slows down the rate of decomposition of the carbon that's a little bit below the surface.
Yep.
All right, well, I might need to wind it up. I really appreciate you guys having this discussion, and all the participants having a discussion too. So we've gone 15 minutes over time, so I apologise for that, but I didn't want to stifle the great discussion we were having, and so thanks for hanging in there for those of you who were able to. Thanks very much to Lynn and Richard and Andy for making yourselves available to present to the group. It's been a really wonderful morning / bit of the afternoon, and the feedback that we're getting through the chat has been really great as well, so really appreciate your time. And for the guys within the community of practice, our next catch up will be at the end of March, although we might talk to Richard about, the possibility of maybe we were wanting to get to the CSBP to have a look at the soil testing facility, so we might just see what and Andy's kindly offered if we wanted to go down and have a look at CWise and the processing of the compost down there, then that's an opportunity as well. So we might just keep in touch and see what we might be able to work in this strange old COVID land that we're living in at the moment. But we'll do what we can do, and we'll be agile and all that sort of thing. So thank you all very much for participating, and I'll hang on the line. So if anyone's got any questions or queries for me, I'll just hang on until it runs off. But I'm happy to have a chat with anybody along the way. So.
And I'll send the files to you now. I'll sit here and fix.
Okay. Great. Okay. Thanks so much, Lynn. See you.
Thank you.
Yeah, thanks. See you, everyone.
Yep.
Thanks, Richard.
Bye-bye.